GCE Advanced Level Chemistry Practical Series Experiment number 28, Examination of the Properties of Carboxylic Acids. In this experiment, we are going to observe how carboxylic acids react with water, sodium hydroxide, sodium carbonate and sodium bicarbonate, how it reacts with alcohols such as ethanol, and we are going to observe how carboxylic acids react with oxidizing agents such as acidified potassium permanganate. Now, let's take a look at the aim that they have listed down here. Aim of this experiment is to observe the chemical properties of carboxylic acids. Just like I said, so we are going to observe how it reacts with many different compounds. Introduction. Organic compounds with the carboxylic acid functional group are known as carboxylic acids. So any organic compound that contain the carboxylic acid functional group. So what is the carboxylic acid functional group? The COOH group. Any carboxylic acid or any organic compound that contains the carboxylic acid functional group is known as a carboxylic acid. Carboxylic acids are found in many natural sources, and carboxylic acids give a sour taste to many food. They are weak acids and dissociate partially in water. So keep in mind, students, this is very important. Carboxylic acids are weak acids. Carboxylic acids, unlike mineral acids, are weak acids. When they are introduced into water, carboxylic acids do not fully dissociate in water. They only partially dissociate in water. Carboxylic acids are compounds containing the carboxyl group, which is the COOH group, which contains a carbon-oxygen double bond and an OH group. A carbon-oxygen double bond and an OH group is there. So we can indicate the presence of a carboxylic acid group like this. So any organic compound that contains this group is referred to as a carboxylic acid. Carboxylic acids are generally more acidic than other organic compounds containing OH groups such as alcohols, but weaker than common mineral acids. Now students, over here you can clearly observe, we know that carboxylic acids are not very acidic. They are weak acids. They don't even fully dissociate in water. So therefore, they are definitely less acidic compared to mineral acids such as HCl. However, carboxylic acids are more reactive than alcohols. They are more reactive than phenols as well. Carboxylic acids are more reactive than alcohols and phenols. Now let's move on to the next slide. Physical properties of carboxylic acids. Carboxylic acid group is a polar functional group. It contains polar bonds, and due to the shape that it has, the overall group is a polar group. You can see if you draw a carboxylic acid functional group like this. Let's draw RCOOH like this. Oxygen is quite electronegative, so it has the delta negative charge here. Over here it will be delta positive. And again, compared to oxygen and carbon, carbon is less electronegative, so therefore carbon is going to be delta positive. This oxygen is also delta negative. Now students, you can see this group is a polar functional group. It is not having a non-polar group, or it does not contain any non-polar bonds. All of the bonds that you see over here are polar bonds, and it contributes to forming a polar functional group. Due to the polarity of the carbon-oxygen and oxygen-hydrogen groups, it forms intermolecular hydrogen bonds. So this is very important. They are capable of forming intermolecular hydrogen bonds. Carboxylic acids are capable of forming dimeric structures in which carboxylic acid molecules are attached by hydrogen bonds as pairs. So carboxylic acid molecules are attached by hydrogen bonds as pairs. Now what this means is, unlike other molecules, for example, if you take alcohols, they too are capable of forming hydrogen bonds. However, carboxylic acid groups go a step further and form dimeric structures, what we call carboxylic acid dimers are formed. These are formed due to forming hydrogen bonds between two carboxylic acid groups, which contribute to forming a dimer like this. Now students, when a dimer like this is formed, you can see where the hydrogen bonds are. You can see where the hydrogen bonds are. This is a hydrogen bond, and there's another hydrogen bond over here. So these two hydrogen bonds keep these two carboxylic acid molecules strongly attracted to one another, forming a dimer. Compared to other organic substances that have OH groups, such as alcohols, you will see they are not capable of forming dimers. Therefore, compared to alcohols, carboxylic acid groups, or carboxylic acids in general, have a higher boiling temperature. Carboxylic acids have a higher boiling temperature due to forming these types of dimeric structures. Dimeric structure of carboxylic acid due to hydrogen bonding is indicated here. Due to these reactions, or due to these reasons, carboxylic acids show higher boiling points than alcohols, aldehydes, and ketones with comparable relative molecular masses. So compared to alcohols, aldehydes, and ketones, and even esters. Esters are quite volatile actually. So you can see carboxylic acids are going to have higher boiling points. So out of all of these organic substances that contain oxygen, such as alcohols, aldehydes, and ketones, and even esters, carboxylic acids have a higher boiling point. Solubility. Now this is also a very important point. Solubility of carboxylic acids. Now when it comes to solubility, carboxylic acid groups, since they have the OH group, they can form hydrogen bonds with water. But you will see when we are carrying out this experiment, certain carboxylic acids do not dissolve in water. So you should ask why some carboxylic acids dissolve in water and some do not. So in this paragraph also, you will come to learn that due to formation of hydrogen bonds with water, carboxylic acids dissolve in water, especially the carboxylic acids that contain 1 to 4 carbon atoms. Carboxylic acids in their homologous series carboxylic acid that contain 1 to 4 carbon atoms in the molecule dissolve well in water. When the number of carbon atoms increase, the solubility decreases. When the number of carbon atoms increase, the solubility of carboxylic acids in water decrease. Aromatic carboxylic acids are water insoluble and exist as a solid crystalline substance. Almost all carboxylic acids are soluble in organic solvents. Now, organic solvents are nonpolar substances. Each carboxylic acid has a nonpolar group. So therefore, almost all of them are soluble in organic solvents. Now, let's explore this point a bit further. Now, we said small chain carboxylic acids such as acetic acid or ethanoic acid. Acetic acid is the common name, ethanoic acid is the IUPAC name. In this case, this carbon chain contains only 2 carbon atoms. And you can see this region is polar, and they are capable of forming hydrogen bonds with water. And the carbon chain is non-polar. This is polar, and this carbon chain is non-polar. As you increase the number of carbon atoms in the carboxylic acid molecule, the nonpolar region becomes larger. For example, if you take a carboxylic acid such as benzoic acid that contains a benzene ring. As you know, benzene rings contain 6 carbon atoms, and benzene is insoluble in water. If you take benzoic acid, it has a large carbon group, or we can say a benzene ring. This section of the molecule is going to be non-polar. If you take this region of the molecule, that is going to be polar. However, in this molecule, a large portion of it, altogether 7 carbon atoms, are going to create a non-polar environment. And there's a small region, the carboxylic acid group, which is going to be polar and which is capable of forming hydrogen bonds in water, which will happily dissolve in water. This region, the polar region, is hydrophilic, and the carbon chain is hydrophobic. So as you increase the number of carbon atoms in a carboxylic acid, the solubility of the carboxylic acid decreases. This is happening as you increase the carbon chain's length, or as you increase the carbon atom or number of carbon atoms in a carboxylic acid molecule. The carboxylic acid molecule progressively becomes more non-polar, or the non-polar region of the carboxylic acid becomes large enough to make the molecule insoluble in water. However, carboxylic acids with even larger carbon chains are easily soluble in organic solvents, non-polar organic solvents. I hope this section is clear to you why carboxylic acids are soluble in water when it comes to carboxylic acid that contain 1 to 4 carbon atoms. They are easily soluble in water. However, as the carbon atom number increases in the carboxylic acid molecule, they become less and less soluble in water, or increasingly less soluble in water. Reactions of alcohols, phenols, carboxylic acids with sodium hydroxide, sodium carbonate and sodium bicarbonate. Students, we have to have an idea when it comes to talking about the acidity of carboxylic acids. We need to figure out whether they are more acidic than phenols and more acidic than alcohols. So let's take a look at some reactions and figure out whether carboxylic acids are more acidic than these other compounds that we have here. We have already studied alcohols and phenols. We know phenols and alcohols are actually less acidic than carboxylic acid. However, let's take a look at these reactions. When you are reacting an alcohol with metallic sodium, sodium hydroxide and sodium carbonate, you will observe that alcohols only react with metallic sodium. Alcohols are not acidic enough to react with sodium hydroxide or sodium carbonate or sodium bicarbonate. Alcohols are only acidic enough to react with metallic sodium. And as they react, they will form their alkoxide anion. And of course, sodium plus ions. We can say they form sodium alkoxides. When it comes to sodium hydroxide, no reaction. When it comes to sodium carbonate, sodium bicarbonate, no reaction. When it comes to phenols, phenols are more acidic compared to alcohols. Phenols are more acidic compared to alcohols. This is due to the phenoxide anion being produced when hydrogen is removed from phenol happens to be more stable than the phenol itself. So therefore, phenols are capable of removing the H plus or removing the hydrogen on the OH group and forming phenoxide anion. So as phenols react with metallic sodium, just like when it comes to reacting alcohols with metallic sodium, hydrogen gas is going to be released. When it comes to phenol also, hydrogen gas is going to be released when sodium reacts with phenol, forming sodium phenoxide or sodium phenolate. You can see when phenoxide ion is formed in the presence of sodium, you will form sodium phenoxide. And when it comes to the reaction with sodium hydroxide, you will form the same compound. You will form sodium phenoxide reacting with sodium hydroxide as well. So, unlike alcohols, phenols are capable of reacting with sodium hydroxide as well. Unlike alcohols, alcohols do not react with it. And when you're talking about sodium carbonate, phenols are not acidic enough to react with sodium carbonate or sodium bicarbonate. Phenols are not acidic enough to react with either one of those compounds, sodium carbonate or sodium bicarbonate. However, phenols are acidic enough to react with metallic sodium and sodium hydroxide. Carboxylic acids, on the other hand, is the most acidic out of the three compounds that we have here, because we can see it reacts with sodium, it reacts with sodium hydroxide, and it reacts with sodium carbonate and sodium bicarbonate. When it reacts with sodium, just like in the previous two cases, you will see hydrogen gas being produced along with sodium ethanoate or sodium ions being formed along with the carboxylate anion. So carboxylate anion will be formed along with sodium plus ions. When it comes to sodium hydroxide, again, it will react with aqueous sodium hydroxide and will form the carboxylate anion. Carboxylic acid will release an H plus and will form the carboxylate anion, forming sodium ions alongside forming the carboxylate anion. So you will have these products formed when the reaction proceeds with sodium hydroxide. So the products are carboxylate anion along with sodium plus ions. When you're reacting a carboxylic acid with sodium carbonate contains sodium plus ions and carbonate ions. Sodium bicarbonate will contain sodium plus ions and bicarbonate ions. Carbonate ions or bicarbonate ions can receive H pluses and get converted into carbonic acid. Carbonic acid is unstable in water, so therefore carbonic acid will turn into carbon dioxide and water. So if carbonate ion or bicarbonate ion receive H plus from an acid, it will turn into carbon dioxide and water. So if the carboxylic acids that we introduce are acidic enough to react with sodium carbonate, you will see the formation of carbon dioxide and water. So carbon dioxide will be observed as formation of bubbles, odorless, colorless gas will be formed here, which is carbon dioxide. Carboxylate anion and sodium plus ions will also be formed. Right, students. So now with that information, we can come to this conclusion. Alcohols are the least acidic. Then we have phenols, and then we have carboxylic acids. So out of the three compounds that we see here, alcohols, phenols, and carboxylic acids happen to be the most acidic. Now let's dive into our experiment. In this experiment, we are going to need, or to conduct this experiment, we are going to need the following chemicals and equipment. The equipment we need are conical flasks, test tubes, boiling tubes, and beakers. As chemicals, we'll be needing concentrated sulfuric acids, ammoniacal silver nitrate. Now, what is ammoniacal silver nitrate? Ammoniacal silver nitrate is basically Tollens reagent. Acidified potassium permanganate solution, methanoic acid, ethanoic acid, benzoic acid, sodium carbonate, sodium hydroxide solution, and sodium bicarbonate solution. So students, keep in mind when you write methanoic acid and ethanoic acid, sometimes we address them by their common name. Methanoic acid is referred to as formic acid, and ethanoic acid is referred to as acetic acid. So please don't get confused when we are referring to methanoic acid as formic acid. Formic acid is a common name for methanoic acid. For ethanoic acid, the common name is acetic acid. You should be familiar with acetic acid because we do use acetic acid at home, because acetic acid is a component in the vinegar that you use. Vinegar contains acetic acid. Now with that information, let's move on to the next slide. So we are going to be taking a look at the steps that we use to conduct this experiment. The first test is testing the solubility of carboxylic acids. We are going to test the solubility of carboxylic acids. Mix 1 cubic centimeter of methanoic acid, ethanoic acid, and benzoic acid with 1 cubic centimeter of water. So we take 3 test tubes and get these acids and mix them with water. And we are going to observe whether these carboxylic acids are completely miscible, whether it mixes completely with water without forming two layers. So that is going to be our observation. We need to observe whether when we are mixing these two compounds together, or when we're mixing carboxylic acids with water, whether they mix to form a single layer without forming two layers. So we have taken formic acid. Like I mentioned, the IUPAC name of formic acid is methanoic acid. If you take formic acid and add water to it and then mix it, you add water to methanoic acid and then you mix the two together, you will not see a layer separation. There is no layer separation. So the methanoic acid is actually soluble in water. The methanoic acid is soluble in water. How do we observe that it is soluble in water? If it was not soluble in water, students, the organic layer and the aqueous layer will appear as two layers. They will not appear as one single layer like this. They will separate into two layers. So since we do not observe two layers here, we can say that formic acid is soluble in water. In fact, we knew this. We knew that carboxylic acids that contain up to 4 carbon atoms are soluble in water. That means methanoic acid, ethanoic acid, propanoic acid and butanoic acid. Up to that point, the carboxylic acids that we have from methanoic to butanoic are soluble in water. Then we have ethanoic. We already know the answer to this. If you take a small amount of ethanoic acid and add water to it and mix it, you are going to observe only one layer. Ethanoic acid is completely miscible in water. So therefore, you can say there is no layer separation. You will see no layer separation, which indicates that acetic acid or ethanoic acid is soluble in water. Now we come across benzoic acid. Now benzoic acid, how many carbon atoms do you see in benzoic acid? It has an aromatic group or benzene ring. So benzene ring itself contains 6 carbon atoms. Altogether it has 7 carbon atoms. Anyway, we know benzene is not soluble in water. So when you have such a large group that is insoluble in water, what happens to the carboxylic acid? Although there's a small section of the carboxylic acid, which is the functional group of the carboxylic acid that is soluble in water, the majority of the molecule is insoluble in water. Then what happens? You will see the entire molecule is not going to be soluble in water. So benzoic acid, as we discussed before, is not going to be soluble in water. Benzoic acid is insoluble in water. So normally in the lab, you obtain benzoic acid as white color needle-like crystals. So if you take small amount of benzoic acid and add water to it and try to dissolve it, you will observe that the crystals, white crystalline solid that you have in your test tube, does not get dissolved. So you will observe that this white color crystals that you have, they will not form a solution when water is added to it. So therefore, this indicates that benzoic acid is insoluble in water. Let's take a look at the statement here. White color benzoic acid crystals remain undissolved when added with water. This indicates benzoic acid or aromatic acids in general are not soluble in water. Now we move on to the second stage of our experiment, which is reacting the carboxylic acids we have taken. Now we took 3 carboxylic acid in the first step. We took methanoic acid, ethanoic acid and benzoic acid. Keep in mind, students, throughout this experiment, we will be taking methanoic, ethanoic and benzoic acid. So we are going to react each of these acids with sodium hydroxide. Now, in the introduction of this experiment, we discussed that carboxylic acids react with sodium hydroxide. So what can you predict when we add sodium hydroxide to these carboxylic acids? They will definitely react with sodium hydroxide. So if you take aqueous sodium hydroxide and react with the carboxylic acids that we have, which is methanoic, ethanoic and benzoic, unlike when added with water, all of these will react with aqueous sodium hydroxide to form a single layer. There will be no layer separation. Why won't there be any layer separation? Because the acids that we have here will react with sodium hydroxide. So let's take a look at the steps. Take a small sample of methanoic, ethanoic and benzoic acid into 3 separate test tubes. Then mix well with 2 cubic centimeters of dilute sodium hydroxide solution. Now students, we are talking about a dilute aqueous sodium hydroxide solution, which means there is water. The medium that sodium hydroxide is present in is water. Observe whether a clear solution is obtained. So we need to observe whether a clear solution is obtained, or whether there is going to be layer separation, or whether there is going to be some undissolved solid in the test tube. So let's take a look at acetic acid. Let's take a look at formic acid. What we have here is methanoic acid or formic acid. So when you take a small amount of formic acid and react with sodium hydroxide, you are going to see formation of a clear solution. No precipitate, no layer separation. That is because 1. Formic acid dissolves well in water. 2. Formic acid reacts with sodium hydroxide. So formic acid, the IUPAC name for the formic acid is methanoic acid. So you can see you form sodium methanoate. So we have formic acid here or methanoic acid here. So methanoic acid, when reacted with sodium hydroxide, will form sodium methanoate or sodium formate. Sodium formate is the common name. The IUPAC name would be sodium methanoate. Sodium methanoate. Sodium methanoate would be the name when you react methanoic acid with sodium hydroxide. The compound that is formed here, or the solution that is formed here, contains sodium methanoate. So students, a clear colorless solution is formed when methanoic acid is reacted with sodium hydroxide. This is because carboxylic acids react with sodium hydroxide. And if you take ethanoic acid, what we have here is ethanoic acid. If you react ethanoic acid with sodium hydroxide also, as we know, since carboxylic acids react with sodium hydroxide, you will form sodium ethanoate. So what we have formed here is sodium ethanoate. sodium ethanoate is going to be formed. So students, again, sodium ethanoate is formed from ethanoic acid. Sodium ethanoate is soluble in water. We have the ethanoate ion along with sodium ion. So this ethanoate ion is soluble in water. So therefore what you observe is a clear solution. There's no layer separation. And we know ethanoic acid in general dissolves in water, and when it reacts with sodium hydroxide in aqueous medium, you form sodium ethanoate, which is going to give us a clear solution. So the reaction is also given here. Apart from the formation of sodium ethanoate, you can see water molecule is also formed because this is a neutralization reaction between a weak acid and a strong base. Sodium hydroxide being the strong base and ethanoic acid being the weak acid. So you will see, apart from a salt being formed, which is our sodium ethanoate salt, and apart from that, a small amount of water or water molecule will also be formed. Now, we observed when water was added to benzoic acid did not dissolve in water. However, if sodium hydroxide is added, so this is aqueous sodium hydroxide. Keep in mind this contains a lot of water. Still, when sodium hydroxide is added, you do not see a layer separation. You do not see the benzoic acid crystals remaining at the bottom of the test tube. So what is the reason for this? As I mentioned earlier, carboxylic acids react with bases, or any acid for that matter, any carboxylic acid for that matter, will react with a strong base such as sodium hydroxide. So when benzoic acid reacts with sodium hydroxide, it forms, so we have benzoic acid, it forms carboxylate anion, which is going to be benzoate ions. So sodium benzoate, we form here sodium benzoate. So the benzoate anion that is formed is soluble in water. So therefore, sodium benzoate is forming a clear solution. It is soluble in water, so therefore it forms a clear solution. Benzoic acid, on the other hand, is not soluble in water. Benzoic acid is going to remain as white color crystalline solid if only water is added to dissolve this. But if sodium hydroxide is added, carboxylic acid that we have here, which is benzoic acid, will react with sodium hydroxide to produce sodium benzoate. So students, the reaction is given here. Due to the formation of the benzoate anion, you are going to see that benzoic acid is going to dissolve in water due to the formation of the benzoate anion. A clear colorless solution is formed when benzoic acid reacted with sodium hydroxide. This is because carboxylic acids react with sodium hydroxide. Now, another clear observation that we can obtain is taking this sodium benzoate solution and reacting it with a strong acid like HCl. So we have HCl added to sodium benzoate salt. We have the sodium benzoate solution previously made in the step that we discussed earlier. So we have the sodium benzoate there, and to that sodium benzoate solution, we are going to add HCl, which is a strong acid. Then sodium benzoate, or the benzoate ion, again will obtain a H plus and will convert into benzoic acid. So as benzoic acid gets formed again, you are going to observe the formation of a white color precipitate. So why a white color precipitate formed again? Because when H plus is taken in by the benzoate anion, it converts into water insoluble benzoic acid. So this benzoic acid that is formed is water insoluble. So it reforms the white crystalline solid, which is going to appear as a white color precipitate. If you again react it with sodium hydroxide, you will observe the formation of sodium benzoate, which is soluble in water. So the solid will again dissolve to form a clear solution. Now students, when you are carrying this experiment out, you need to understand why the benzoate ion actually takes in an H plus. So to understand this, you need to remember the theory part, where when a weak acid's salt is reacted with a strong acid, the weak acid salt get converted into the weak acid and gets displaced. Or in other words, the weak acid's anion gets displaced as the weak acid in the presence of a strong acid. So in the sodium benzoate medium, we have benzoate anion, which is an ion formed by a weak acid. So to a medium that contains an ion that is formed by a weak acid, if you introduce a strong acid like HCl, the strong acid is capable of displacing the weak acid. So you will see the strong acid will give an H plus to the anion of the weak acid and displacing this anion of the weak acid as the weak acid itself. So keep in mind students, whenever an acid is displaced, that is because a stronger acid was reacted with its anion. So a weak acid, it gets displaced when its anion is reacted with a stronger acid. So out of these two, HCl and carboxylic acid, which one is stronger? HCl for sure. The reason for that is because HCl was capable of displacing the benzoic acid when reacted with the benzoate anion. Again, something to keep in mind. So this is why we observe this particular reaction. When you are reacting the sodium benzoate with HCl, you will form carboxylic acid again, which is benzoic acid, which will be precipitating out as a white color precipitate. Reaction 3, which is going to be the reaction where we are reacting the carboxylic acids with sodium carbonate. They can react with sodium bicarbonate as well. You will have the same observation. When you take a small sample of these three acids into test tubes, and if you add to them 2 cubic centimeters of dilute sodium carbonate solution, they are asking us to observe the evolution of gas bubbles. The formation of gas bubbles is what they are asking us to observe. Let's see the reaction that takes place. If you take a carboxylic acid, now in this case we have taken methanoic acid. If you take a carboxylic acid and react with sodium carbonate, you will be forming, in this case, sodium methanoate, carbon dioxide, which is why we are observing gas bubbles actually, and water. Now this is a reaction between a basic salt and a weak acid, so we are going to have water formed as well. So in this reaction, or carboxylic acid to carbon dioxide ratio is going to be 2:1. You can see carboxylic acid, there are 2 molecules here, and the amount of carbon dioxide produced is just 1. So that is another observation that you need to make here. Now students, one of the other things that I want you to keep in mind is that when this reaction is happening, sodium carbonate, if you take sodium carbonate in aqueous medium, actually turns into sodium plus ions, 2 aqueous sodium plus ions, and 1 carbonate ion. These are all in aqueous medium, so all of these ions are also aqueous. So when the carbonate ion, now carbonate ion is an ion formed by a weak acid, carbonic acid. So when the carbonate ion is in the presence of a bit of a stronger acid than carbonic acid, which is in this case formic acid. Formic acid is capable of releasing its H pluses to react with the carbonate and turn it into carbonic acid. So since there are 2 negative charges, 2 H pluses are required to convert the carbonate into carbonic acid. H2CO3, and methanoate ion will also be formed. Methanoate ion will also be formed. When I write methanoic acid like this, you have to keep in mind the actual structure is this, right? That's why I wrote the methanoate ion in this way. However, students, when you have formed your carbonic acid, it is unstable. So this carbonic acid actually decomposes to form H2O and carbon dioxide. You don't actually observe just carbonic acid. Carbonic acid is unstable. It will completely dissociate or decompose to form water and carbon dioxide. So the observation of forming gas bubbles confirms that in the presence of formic acid, carbonates were converted into carbonic acid. What does this tell us? This tells us that the formic acid was a stronger acid than carbonic acid, because you can see this weak carbonic acid's anion, which is the carbonate anion, which is the weak acid's anion, was displaced by another acid. In this case, formic acid was able to take this anion, carbonate anion, and displace it as carbonic acid. So out of these 2 acids, out of the carbonic acid and the formic acid, which one was stronger? Formic acid was stronger. So here, the formic acid represents all carboxylic acids, because all carboxylic acids are capable of reacting with these carbonate ions and displacing carbonic acid, which is normally observed through the formation of carbon dioxide bubbles. So therefore, students, you need to keep in mind carboxylic acids are stronger acids compared to carbonic acids. That is why carbonates or even bicarbonates are displaced as carbonic acid. Now, you can see here, reaction with sodium carbonate when methanoic acid or formic acid is reacted with sodium carbonate, you can see the formation of gas bubbles. I'm not sure whether the camera captures it, so I will draw it again. So there are gas bubbles that are drawn here, which indicates that the carbon dioxide gas is evolved. So by looking at this diagram, or by when you are doing this experiment in the lab, by looking at the test tube, you would know whether it is carbon dioxide that is released. Only thing that you observe is a colorless, odorless gas is evolved. So the observation would be a colorless, odorless gas is evolved, right? But since we know the reaction, we can say that the gas that is evolved here is carbon dioxide. But if a question is asked, what the observation is when sodium carbonate is reacted with a carboxylic acid, the observation would be just the formation of a gas, or gas bubbles are evolved. Other than that, you should not go to the extent of writing carbon dioxide gas bubbles are evolved, because you don't see these bubbles labeled carbon dioxide. You don't see the carbon dioxide gas bubbles formed, or inside the bubble you don't see carbon dioxide written in it. So therefore you can't say as an observation what you observe is the formation of carbon dioxide gas bubbles. You have to say you will see gas bubbles being formed. That is your observation. So students, that is an important point to keep in mind. When a carboxylic acid is reacted with sodium carbonate, you will see the evolution of a gas, or gas bubbles being formed, or you can say effervescence is observed. Evolution of gas bubbles observed. The gas that evolved is carbon dioxide. We know this because we have the reaction with us. Ethanoic acid and benzoic acid will react similarly and will form bubbles due to formation of carbon dioxide as a product. So this particular reaction is not applicable only to methanoic acid. Any carboxylic acid reacts with sodium carbonate or sodium bicarbonate and will release carbon dioxide. Students, in fact, we actually use this test as an identification test for carboxylic acids. We know if we have compounds that are containing OH groups or oxygen in general, if you have a phenol, if you have alcohol, and if you have carboxylic acid, if you want to separately identify the three of them, or separately identify the carboxylic acid from the three of these compounds, the easiest test to be done is adding sodium carbonate to a small sample of each of those compounds, because alcohols and phenols are not strong enough to react with sodium carbonate. They are not strong enough to react with sodium bicarbonate as well. So therefore, we actually use addition of sodium carbonate as a test to identify the presence of a carboxylic acid. So we are going to further study the reaction between the carboxylic acid and sodium carbonate. When a carboxylic acid reacts with sodium carbonate, the OH bond will break to release H plus ions. So you can see, if you take a carboxylic acid, there's a bond between oxygen and hydrogen. This oxygen-hydrogen bond is a polar bond, and in water, actually, these carboxylic acids dissociate into forming carboxylate anion and H plus. So, which means the O and the hydrogen bond, OH bond, actually breaks when the weak acid, which is carboxylic acid that we have here, dissociates in water. So this is a partial dissociation. That's why we have these reversible arrows. The carbonate ions that are in the medium, so when you add sodium carbonate to this particular solution of methanoic acid, the carbonate ions in the medium will react with the H plus ions forming carbonic acid, which I mentioned earlier. Since the carbonic acid is unstable, very important, it will decompose to form carbon dioxide and water. It will decompose to form carbon dioxide and water. We looked at that in the previous slide, right? We looked at it. So when carbonate ion reacts with formic acid or methanoic acid, it will form carbonic acid and methanoate ion. So our main focus is in the carbonic acid. Carbonic acid that is formed here is unstable, so it will decompose to form water and carbon dioxide. Revisiting the same point. Now we can see carboxylic acid when reacted with the carbonate ion. The H plus released from the carboxylic acid. The carbonate ion will react to form carbon dioxide and water. So carbon dioxide and water is actually formed due to decomposition of H2CO3, which is our carbonic acid. Right, so keep in mind this carbon dioxide and water is observed due to the decomposition of the carbonic acid that was formed. For the above reaction to happen and for carbonic acid to be displaced, the carboxylic acid should be more acidic than the carbonic acid. Again, students, we discussed this point earlier as well, but take note of this. This is very important. Students, for the carbonic acid to be displaced, the carboxylic acids we use should be more acidic than the carbonic acid. Don't get confused. Carbonic acid is H2CO3, and we are referring to these types of acids that we have here as carboxylic acids. Carboxylic acids are acids that contain this group. Carbonic acid is basically H2CO3. Similar names, so please don't get confused. This is carbonic acid. This is unstable, so it decomposes to form H2O and water. H2O and carbon dioxide. Right, so now the main point that we were addressing here is the fact that the carboxylic acids should be strong acids compared to carbonic acid. Otherwise, the displacement of carbonic acid is not going to take place in the presence of a carboxylic acid. General reaction with carboxylic acids, we can see sodium carbonate. Sodium carbonate would react with any carboxylic acid to form a sodium carboxylate compound, one carbon dioxide and one water molecule. However, the ratio between sodium carbonate and carboxylic acid is going to be 1:2. So with one sodium carbonate, two carboxylic acids will react to form carbon dioxide and water. Reactions where the OH bond in carboxylic acids are broken. So in each of these reactions, you can see the OH bond. The OH bond is broken. So when you're reacting a carboxylic acid with sodium, we saw the formation of a sodium carboxylate salt and hydrogen gas. So in this reaction, the observation is the formation of a hydrogen gas. So at that point, with two sodiums, two carboxylic acids will react, and then we observed carboxylic acid reacts with sodium hydroxide. We conducted this practical, or we actually discussed the theory parts relating to sodium hydroxide reacting with carboxylic acids. Will form a sodium carboxylate salt and water. Again, when sodium carbonate reacts with carboxylic acid, you will form a sodium carboxylate salt and carbon dioxide and water. So the carbonate group that we have here will take up 2H plus ions and will turn into carbonic acid, which will break into carbon dioxide and water. Similarly, when you are talking about the bicarbonate or sodium bicarbonate is also capable of taking an H plus and forming the same acid, which is H2CO3 carbonic acid. And the carbonic acid will decompose into forming carbon dioxide and water. So when it comes to bicarbonate, since there's already an H attached to the carbonate ion, you only need one more hydrogen or one more H plus from the carboxylic acid to form the carbonic acid, which will decompose to form carbon dioxide and water. With that, we move on to oxidation reactions. Reaction with oxidizing agents such as acidified potassium permanganate or acidified potassium dichromate. In this experiment, we are only asked to use potassium permanganate, acidified potassium permanganate. However, we can use acidified potassium dichromate as well. Take small sample of methanoic acid, ethanoic acid and benzoic acid into 3 separate test tubes. Add acidified potassium permanganate solution into this mixture and observe whether a color change occurs. You need to observe whether there is a color change. Now, acidified potassium permanganate is a very familiar substance for us. Why? Because we use this strong oxidizing agent quite often in the lab. Acidified potassium permanganate is purple in color. If it actually oxidizes something, acidified potassium permanganate will lose its color as permanganate ions, which are purple in color, will get converted into Mn2+. Although Mn2+ aqueous ions are pale pink, we normally observe those solutions as a colorless solution. So, acidified potassium permanganate will lose its color, or it goes from purple to colorless, when it is actually used up to react with a substance that actually undergoes oxidation. Then we have acidified potassium dichromate. Acidified potassium dichromate is orange in color. Normally, to acidify these solutions, we use sulfuric acid. So, as we use acidified potassium dichromate as an oxidizing agent, if acidified potassium dichromate actually oxidizes another group, the dichromate ion reduces to chromium 3+. So, the orange color solution turns into a green color solution. Let's take a look at the statement that is written here. The carboxylic acid do not get further oxidized. The carboxylic acids do not further get oxidized in the presence of oxidizing agents such as acidified potassium permanganate or acidified potassium dichromate. So they do not further get oxidized. However, methanoic acid has an aldehyde group. So as you know, students, alcohols and aldehydes can get oxidized easily with acidified potassium permanganate and acidified potassium dichromate. So therefore, if an aldehyde group is present in one of these carboxylic acids, they are capable of reacting with that aldehyde group and oxidizing it. So they say formic acid or methanoic acid. Methanoic acid is the only acid that get oxidized in the presence of these oxidizing agents. So methanoic acid has an aldehyde group that gets oxidized in the presence of an oxidizing agent mentioned above. So let's take a look at methanoic acid. So students, if you take a look at the methanoic acid has a group that is capable of reacting with an oxidizing agent, which is an aldehyde group. Therefore, in the presence of acidified potassium permanganate or acidified potassium dichromate, you can actually oxidize methanoic acid. But can the other carboxylic acids get oxidized like this? Not at all, because other carboxylic acids, starting from ethanoic and upwards, they do not contain any aldehyde groups. Only methanoic acid contains an aldehyde group like this. So therefore, other carboxylic acids do not get oxidized in the presence of oxidizing agents such as this one. However, methanoic acid can turn acidified potassium permanganate colorless, or the purple color of acidified potassium permanganate turns colorless. When it comes to acidified dichromate, it is orange in color. You will see it forming a green color solution. Green color solution is due to the formation of a complex ion such as this one. Chromium 3 plus ion normally with one sulfate ion, because we used sulfuric acid to acidify the medium. One sulfate ligand and 5 water molecules can form a green color complex, which is the reason for us to observe the color change from orange to green. So formic acid does react with these oxidizing agents and show a color change. And actually the reaction is also written here. The ionic reaction or half reactions are given here. If you take formic acid and react it with the oxidizing agent, due to the presence of the aldehyde group, formic acid will undergo oxidation to form carbon dioxide. Carbon dioxide will be formed. So since you have two oxygens here and two oxygens here, no problem when it comes to the balancing of the equation. Oxygens are already balanced, carbons are already balanced. However, hydrogens are not balanced, so you will add two hydrogens to the right hand side of the equation. So after adding two hydrogens, although the atoms are balanced, the charges are not balanced at this point. We have two positive charges on the right hand side and no charges on the left hand side. So to balance the charges, we can add two electrons to the right hand side. Now students, you can see the electrons are present on the right hand side, indicating the electrons were removed. This is the oxidizing or oxidation reaction. And we know permanganate ions turn into Mn2+. And on the left hand side, there are 4 oxygen atoms to balance off the 4 oxygen atoms. On the right hand side, we have added 4 water molecules. Now 4 water molecules will help us balance the oxygen atoms. However, it introduces 8 hydrogen atoms. On the left hand side, we don't have any hydrogen atoms. So to balance off the hydrogen atoms, we can add 8 H+. So at this point, you will see the atoms are balanced. However, the charges are not balanced. So if you take a look at these two sides, on the right hand side, the overall charge of this particular reaction is +2. On the left hand side of this reaction, overall charge, we have +7. At this point, you wouldn't have these electrons. I have already written the balance equation. So keep in mind, the electrons were not added before. When it comes to learning how to balance, electrons will not be there. So hydrogens will bring in 8 positive charges, and there's 1 negative charge. Altogether, the overall charge on the left hand side would have been plus 7. And to bring it to plus 2, which is the charge on the right hand side, we can add electrons to the left hand side. So if plus 7 has to be brought down to plus 2. So how many electrons should you add? 5 electrons. That's why you see the addition of 5 electrons in this particular reaction onto the left hand side. So now it is balanced when it comes to the atoms of this equation as well as the charges. However, when you're trying to write one balanced equation, so these are half equations. The lower one is reduction. The upper equation is oxidation. So equation number 1 releases only 2 electrons, and equation number 2 takes up 5 electrons. So since there's no balance of the amount of electrons that are released and taken in, we have to multiply each of these reactions so that the number of electrons that are released and the number of electrons that are taken in become the same, or these electrons on either side of these equations get cancelled off. So for us to do that, we have to multiply the first equation by 5 and the second equation by 2. First one, when you multiply it by 5, the number of electrons become 10 here. And when you multiply the second equation by 2, number of electrons over here becomes 10 too. So the number of electrons released and absorbed or taken in happens to be the same. Therefore, we can actually finally cancel off the electrons and write the main equation, which happens to be 5 methanoic acid, 6 H plus, 2 MnO4, 5 carbon dioxide, 2 Mn2 plus, and 8 water molecules. This is how you would normally write an equation for if you are given the half equations, or if you know how to write the half equations. You have to make sure the half equations have their electrons properly balanced, and then the electrons released, the electrons taken in when it comes to the half equations should be the same before writing the complete ionic equation. Now students, this is just a image to show how the color changes are normally going to be observed when formic acid is reacted with acidified potassium permanganate and acidified potassium dichromate. So when acidified potassium permanganate is taken into a test tube, it is going to appear purple in color. However, as we add formic acid, since the formic acid gets oxidized in the presence of acidified potassium permanganate, you will form Mn2+. Permanganate ions get converted into Mn2+, which is going to appear colorless. Apart from that, since you can't observe the bubbles that are drawn here on the table, we will draw the bubbles again. This test tube is going to, one of the observations that we're going to observe here in the test tube is formation of gas bubbles. Effervescence will be observed. So formation of gas bubbles is observed due to the formation of carbon dioxide. Formic acid gets converted into carbon dioxide. When it comes to the use of potassium dichromate, dichromate is orange in color. And when dichromate gets reduced to form chromium 3+, the solution is going to be green in color. As dichromate oxidizes formic acid, dichromate ions get reduced to Cr3+, while forming carbon dioxide. So you can see the formation of carbon dioxide bubbles here. So carbon dioxide is formed due to formic acid getting oxidized to form CO2. So students, the color changes are these. Potassium permanganate turns colorless. Potassium dichromate, which is orange in color, turns a green color. Now let's move on to the next slide. What about ethanoic and benzoic acid? Or what about any other carboxylic acid? Carboxylic acids in general do not undergo any further oxidation. If we're talking about organic compounds that contain only one functional group, and if that functional group is carboxylic acid groups, apart from formic acid, all the other carboxylic acids do not undergo oxidation. So acidified potassium permanganate and acidified potassium dichromate will not be able to oxidize these carboxylic acids. So you will not see the formation of carbon dioxide. These oxidizing agents are not capable of oxidizing carboxylic acids except for formic acid. So therefore, no reaction, no changes in color of the solution. Now we come across reaction with Tollens reagent. So the Tollens reagent is a weak oxidizing agent. So we'll take a look at the reaction with Tollens reagent. Take a small sample of methanoic, ethanoic and benzoic acid into 3 separate test tubes. Add 2 cubic centimeters of ammoniacal silver nitrate. So ammoniacal silver nitrate is basically our Tollens reagent. If you remember, Tollens reagent is used to identify the presence of an aldehyde. And then heat in a water bath. After adding these compounds together, you have to heat the mixture in a water bath and observe whether a silver mirror is formed. You have to observe whether a silver mirror is formed. Ammoniacal silver nitrate is a weak oxidizing agent. It's a very weak oxidizing agent. It is not strong enough to oxidize alcohols. It can't oxidize alcohols into aldehydes and carboxylic acids. It can't oxidize ketones. And it can't obviously oxidize carboxylic acids. Not even the strong acidified potassium permanganate is capable of oxidizing carboxylic acids. So alcohols, ketones and carboxylic acids are not going to get oxidized in the presence of ammoniacal silver nitrate or Tollens reagent. However, aldehydes can be oxidized with the use of Tollens reagents. So aldehydes, unlike carboxylic acids, ketones and alcohols, can get oxidized in the presence of Tollens reagent. Although Tollens reagent is a weak oxidizing agent, it can oxidize aldehydes. Since methanoic acid, so methanoic acid we observed earlier has an aldehyde group. Since methanoic acid contains an aldehyde group, it will react with Tollens reagent and form a silver mirror. So students, when it comes to methanoic acid is the first acid in the homologous series of carboxylic acids. So methanoic acid contains the aldehyde group. All the other carboxylic acids in the homologous series does not contain a aldehyde group. So methanoic acid is going to react with Tollens reagent, and the aldehyde group present in the methanoic acid is going to get oxidized into forming a carbon dioxide. Actually, so methanoic acid again turns into carbon dioxide. Other carboxylic acid groups actually do not react with Tollens reagent. So only methanoic acid will react with Tollens reagent, forming carbon dioxide and our silver mirror. So other carboxylic acids will not answer to this test. So you can see we have methanoic acid here, and if you observe here, methanoic acid contains this aldehyde group that can get oxidized in the presence of Tollens reagent. So it will form silver mirror. So silver mirror formation is observed due to the silver plus ions in tolerance reagent getting reduced to form silver solid. And this formed silver solid gets coated in the internal wall of the test tube, forming a silver mirror. That's why we call it the silver mirror test. So when you are conducting this experiment, you will see the internal walls of the test tube getting coated with the silver solid that is formed through this reaction. So a silver mirror is observed along with carbon dioxide that is produced. So we can see a small diagram explaining us what is happening in this reaction. So you have to take tolerance reagent, and to it we are adding formic acid or methanoic acid. And after adding them together, we place the test tube in a water bath and we heat it. So once we heat it, if you allow the reaction to happen for a while, the formic acid gets converted into carbon dioxide. We can say formic acid oxidizes to form carbon dioxide, and ammoniacal silver nitrate, which is having this formula, it contains silver plus ions. As formic acid gets oxidized, silver ions get reduced. So silver ions get reduced to silver solid, and the silver solid that is formed will be coated in the internal wall of the test tube, forming a nice silver mirror. This is one of the most interesting tests that we can do in the lab. The formation of the silver mirror is something that is very interesting to observe. So you can see the formation of the silver mirror when formic acid is added with tolerance reagent and heated in a water bath. Silver mirror formation can be observed. So what about other carboxylic acids? Formic acid, it forms a silver mirror along with carbon dioxide. But all the other carboxylic acids do not react with tolerance reagent to form a silver mirror. So therefore, ethanoic, benzoic acid, if you do the same reaction with the use of tolerance reagent, you will not observe the formation of a silver mirror. So the basic idea behind formation of silver mirror is given here. Tolerance reagent, which is AgNH3 twice 1 plus. This is a complex ion, contains silver plus ions. Bear with me. As the aldehyde group in formic acid gets oxidized, the silver plus ions get reduced to form silver solid. So when an oxidation reaction is happening, where formic acid is turned into carbon dioxide, silver ions get converted into silver solid. The half equation for the reactions are given below. You can see the ammoniacal silver nitrate has this complex ion. So this complex ion contains silver plus ions. Those silver plus ions will get converted into silver solid by taking an electron. And as silver solid is formed, you can see the two ammonia ligands are released. So two ammonia molecules will also be released. Then we have the formic acid, which is going to get converted into carbon dioxide. Now students, when you are writing this equation, I am quite certain that you are very familiar with balancing off an equation in acidic medium. But what about in alkaline medium? So all that you know is this formic acid gets converted into carbon dioxide. So in acidic medium, you know how to balance this by adding H pluses, because you can see the carbon number is balanced oxygen atoms are balanced, hydrogen atoms are not balanced. So in acidic medium, you would normally add H pluses, right? 2 H pluses. Can you do the same here in alkaline medium? No. So instead of adding H pluses, you actually have to not add H pluses. If you're adding H pluses to balance it off, you can actually add an equal amount of OH minuses to cancel off the addition of H pluses, so that what you form here is water, because H pluses will not be present in an alkaline medium due to the high concentration of OH minus ions. They will react to form water. So you can balance this off by adding 2 molecules of water. Instead of writing H plus, you can add 2 molecules of water. So since there are 2 molecules of water on that right hand side, you can see the number of oxygen atoms and hydrogen atoms have now changed. So due to the addition of water, now the number of oxygen atoms have gone up by 2, and the number of hydrogen atoms also have gone up by 2, which means on this side also you have to add 2 hydroxide ions. Or else, as a rule of thumb, you can think, since you are adding 2 OH minus ions onto the right hand side, you can add the same number of hydroxide ions onto the left hand side as well. And as H plus and OH minus react with each other, they form water molecules. So this is the main reaction. So instead of writing 2H plus and 2 OH minuses, you can take 2 water molecules on the right hand side. Now you can see left hand side, the number of atoms are balanced. However, what about the charges? On the left hand side there are 2 negative charges. So to balance off the 2 negative charges, you can add 2 electrons onto the right hand side. So this is how we actually get to the equation that we have here, the second equation. First equation is fairly easy because it is just the reduction of silver plus ions to silver solid. However, the second reaction requires a little bit more knowledge on how to balancing equations in acidic and alkaline mediums. So you can see we have written the equation here. First reaction takes up 1 electron, which is a reduction reaction. Second reaction is an oxidation reaction, releasing 2 electrons. So the number of electrons released and number of electrons taken in are not the same. So therefore, we have to multiply the first equation by 2, and second equation should be added to that. So when you do that, you get your final equation here, written like this. 2 silver ammonia complex plus 2 OH minus and formic acid forms 2 silver solid, 4 ammonia, 1 carbon dioxide and 1 water molecule. So students, you should be able to write an equation like this starting from half equations that we have written here. You should have the skill to write a full balanced chemical equation starting from half equations like this. So now let's move on to the next slide. So in the next slide, they ask us to react each of these carboxylic acids we took, which is methanoic, ethanoic and benzoic, with ethanol with the use of concentrated sulfuric acid as a catalyst. So let's take a look at this step. Take methanoic acid, ethanoic acid and benzoic acid as carboxylic acid for this test, and then take about 1 cubic centimeter of ethanol, add the carboxylic acid to it and a few drops of concentrated sulfuric acid and heat gently for about 1 minute. Pour this mixture into approximately 5% aqueous solution of sodium bicarbonate in a beaker or a watch glass, and note the odor that is observed. So what we're trying to do here is, students, the formation of an ester. As you know, carboxylic acids, when reacted with alcohols, will form esters. Now, esters are, carboxylic acids, alcohols will form esters in the presence of concentrated sulfuric acid as a catalyst, and esters are volatile organic compounds. I mentioned earlier, carboxylic acids are somewhat, or they contain really high boiling temperatures when comparing other organic substances that have a similar molecular mass. When it comes to esters, esters have a lower boiling point. They are volatile substances. So esters are volatile, and they possess a characteristic smell that allows the identification of the formation of an ester. So students, it is very easy in the lab to know if someone is forming an ester. If you have ever worked side by side with a colleague, you would know if that colleague is forming an ester, because as an ester gets formed, it releases a very characteristic smell. Most esters have fruity smells, sweet smells, very pleasant odors. So formation of an ester can be identified by their characteristic smell. Now we have taken three carboxylic acids. We are reacting all three of these carboxylic acids with the same alcohol, which is ethanol. However, students, the ester that is going to be formed is not the same, because we are using ethanol and three different carboxylic acids, and we are going to be forming three different esters. Each ester has its own characteristic smell. Each ester has its own characteristic smell. Sometimes by observing the smell, you can tell what ester has been formed. So let's move on to the reaction that is taking place. So let's take a look at the main reaction. Over here, students, you can see the carboxylic acid. This is a general equation for carboxylic acid and alcohol reaction. So you have three different carboxylic acids. That's why I have taken RCOOH. And we have ethanol. We are using ethanol here in this reaction. So when the carboxylic acid reacts with ethanol in the presence of concentrated sulfuric acid and heat, it forms an ester. And in the carboxylic acid, the OH group completely gets removed, and from the alcohol, the hydrogen gets removed, form a water molecule. These two groups together will form a small molecule, which is a water molecule. So this is a condensation reaction. Now, students, I have gotten many inquiries how you can actually remember which group from the carboxylic acid gets removed along with which group of the alcohol. Sometimes some students think alcohol will give off the OH section of the alcohol, and carboxylic acid will only give hydrogen from here. So sometimes there's confusion revolving around which section of the carboxylic acid and which section of the alcohol actually gets removed when it comes to formation of an ester. An easier way to remember this is by remembering that this is not the only way that we form an ester. We can also form an ester from a derivative of carboxylic acid. So we have acyl chlorides, which is normally derived from carboxylic acids. Acyl chlorides are actually more reactive than carboxylic acids. So if you take acyl chloride and react it with an alcohol like ethanol, the same product will be observed. Along with, instead of water, they will have HCl produced. Now at this point, you can see you do not have an OH group in the acyl chloride. So your concerns about which group is getting removed is put to rest here, because there's no OH group in acyl chloride. So it is very clear that when it comes to this reaction, if you're trying to form HCl as a byproduct, these two groups are the ones that actually got removed when forming the HCl. So students, I hope this helps for you to kind of remember which group from the carboxylic acid actually gets removed along with the hydrogen of the alcohol. So when it comes to a reaction between carboxylic acid and the alcohol, carboxylic acid breaks the bond between oxygen and carbon and remove the OH group. And when it comes to the alcohol, the bond between oxygen and hydrogen is broken, removing a hydrogen. So those OH and hydrogen together will form a water molecule. Another way in which you can produce an ester is by reacting an acyl chloride with an alcohol. Acyl chloride and alcohol together will also form esters by releasing or while releasing a small molecule like HCl. So students, keep this important point in mind. And with this information, we can actually move on to, before moving on to the next slide, actually, we need to discuss the actual reactions that take place here. So we have methanoic acid reacting with ethanol, CH3, CH2OH. When these two react, what we form here is ethyl methanoate. Ethyl methanoate is formed. This is referred to as ethyl methanoate. Ethyl methanoate is formed, and this ester is going to have a rum smell. It smells like rum. So the ester that is formed here would give you a rum smell. After observing the smell of ethyl methanoate, we can actually move on to the next reaction. In the next reaction, we'll take a different color and write down the equation for the next reaction. We are going to react ethanoic acid, CH3, COOH, with CH3, CH2OH. So this is actually a reversible reaction. All of these reactions are going to be reversible. So you form an ester, which is ethyl ethanoate. Let's write the formula of ethyl ethanoate: CH3, C, double bonded O, O, CH2, CH3, along with a water molecule. In the previous instance also, we formed a water molecule. That is something that you should not forget. So in the equation, you can see the formation of the ester along with the water molecule. So the name of this compound is ethyl. Ethyl group is here. And then the main carbon chain would be this. It has 2 carbons. So therefore, after leaving a space, you will write ethanoate. So this is ethyl ethanoate. This is ethyl ethanoate. So the smell of ethyl ethanoate is going to be a sweet, fruity smell. We refer to it as a sweet, fruity smell. So ethyl ethanoate is a sweet, fruity smell that you observe when you conduct this reaction and form ethyl ethanoate. You will see the formation of, or you will observe or note the smell to be a sweet, fruity smell. And finally, we move on to the reaction between benzoic acid and ethanol. Benzoic acid and ethanol in the presence of concentrated sulfuric acid will form ethyl benzoate. Will form ethyl benzoate along with some water. Now, we write the name ethyl benzoate. Now, ethyl benzoate ester has a mix of smells. Sometimes it is considered to be grape smelling. Sometimes it's a mix of smells of wintergreen, medicinal, grape-like smell. So we can actually say it's wintergreen, or sometimes commonly referred to as grape smell as well. So it's a mix between wintergreen, medicinal, grape smell. So students, this is the smell of ethyl benzoate. So the formation of esters can easily be identified by these characteristic smells. So if you are actually forming an ester, you will get this characteristic smell also released when you are conducting this experiment. If there is no characteristic smell that is formed, that means no ester was formed. So you can identify the presence of an ester by its smell. Now let's move on to understanding how we actually conduct this experiment. We will have a water bath set up, and we will have our ethanol in a test tube dipped or submerged in the water bath. You can see we have kept the test tube in the water bath, and we are adding the carboxylic acid to the ethanol. And while adding the carboxylic acid, you can actually add your catalyst, which is sulfuric acid. After adding these reagents together and heating it for a while, you will see the formation of, or you will observe the ester smell. Characteristic smell of the ester will be observed. This is because an ester will be formed here. An ester will be formed here. And esters are volatile substances. So therefore, the ester will, or ester vapor, will fill the environment around the test tube, and you will be able to very clearly notice the smell of the ester. If you are conducting this in a lab environment, you will observe the whole lab environment actually starts to smell like fruits or rum, or sometimes wintergreen grape smells, depending on what experiment you are doing. So usually esters will have a very pleasant fruity smell, and that very pleasant fruity smell will actually fill the lab. So you will know that ester has been formed. Another way to observe the smell that is in the ester very clearly is given here. You can take the ester formed in the previous step and add it to 5% sodium bicarbonate. You can have the 5% sodium bicarbonate in a petri dish, and you can add the ester formed above into this sodium bicarbonate solution. So in this test tube that we have the ester in, it contains sulfuric acid. We use sulfuric acid as a catalyst, so therefore it did not get used up. Sulfuric acid is still present in this test tube. So when you add this mixture of ester and sulfuric acid into sodium bicarbonate will react with the sulfuric acid and will form carbon dioxide and water. And carbon dioxide gas you will see the formation of carbon dioxide gas, and gas bubbles will be evolved from this solution. So as carbon dioxide gas is evolved from the solution, particles of ester will also get carried along with carbon dioxide. So as carbon dioxide takes particles of ester also as a vapor, you will be very clearly able to note the smell of that particular ester. So that's why we add sodium bicarbonate or ester into sodium bicarbonate, so that the carbon dioxide produced can carry along with it small particles of ester or a certain amount of ester, and we can very clearly observe the characteristic smell of ester due to this reason, because carbon dioxide is a colorless, odorless gas. So there's no odor in carbon dioxide. You will not interfere, or the smell of the ester is not going to be hindered due to the presence of carbon dioxide. So therefore, students, this step is just to very clearly note the smell that is released by the ester. With that, students, we conclude the theory parts revolving around this experiment. Now, it is time for us to move on into the lab and conduct these experiments. JCE Advanced Level Chemistry Practical Series, experiment number 28. Examination of properties of carboxylic acids. In this experiment, we will be focusing on observing the chemical properties of carboxylic acids, the solubility of different types of carboxylic acids in water, and the chemical reactions that carboxylic acids are involved in due to their properties will be explored in this experiment. Now, let's move on to the reagents we will be using for this practical. In this practical, we will be using these chemicals. We have methanoic acid, also known as formic acid. We have ethanoic acid, known as acetic acid. We have benzoic acid. We will be using sodium hydroxide, sodium carbonate, carbon tetrachloride. We will be using potassium permanganate, potassium dichromate. We will be using ethanol, concentrated sulfuric acid, sodium carbonate, and silver nitrate. Apart from those chemicals, we will be using test tubes. As you can see, we have labeled these test tubes because we will be adding methanoic acid, ethanoic acid, and benzoic acid into this labeled test tube. So these test tubes are labeled methanoic, benzoic, and ethanoic acid. Apart from those, we will be using a wash bottle containing distilled water. We will be using a water bath setup. You can see here we have a spirit burner, we have a tripod, a wire mesh, and a beaker which we will be using to have a water bath. Now, let's move on to our first part of this practical. In this part of the practical, we are going to observe the solubilities of different carboxylic acids. Like we mentioned earlier, we have here methanoic, ethanoic, and benzoic acid. Each of these carboxylic acids have different numbers of carbon in them. Higher the carbon number, the more likely they can become insoluble in water. Carboxylic acids with shorter chains of carbon are soluble in water. Let's take a look at what observations we will notice when we add water to each of these carboxylic acids. We have here a test tube labeled methanoic acid. To this, let's add a small amount of methanoic acid. As you can see, methanoic acid is a clear acid. It does not have a color. And now we are going to add a little bit of water with the use of a wash bottle. Now we have added a little bit of water to this. As you can see, when I added water into methanoic acid, we did not see a layer separation. This indicates methanoic acid was soluble in water. If you mix it, you can see still you do not see any form of layer separation. Now, our test tube that is labeled ethanoic acid, and to this, let's add a small amount of ethanoic acid. We have here our ethanoic acid bottle. Let's add a small amount of ethanoic acid into this test tube. Ethanoic acid is commonly known as acetic acid, and this is present in vinegar as well. Now, to this, I will be adding a small amount of water. As you can see, just like in the previous example shown, ethanoic acid also dissolves well in water. When I added water, we did not see any form of a layer separation. If you mix it really well, you can see ethanoic acid has mixed really well. You can see upon addition of water to ethanoic acid, we do not see any layer separation. This is because ethanoic acid dissolves well with water. Now, we move on to benzoic acid. We have here benzoic acid sample. Benzoic acid is present as a powder here. So we'll take a small amount of benzoic acid, into our test tube. Now we have taken a small quantity of benzoic acid into our test tube. Now let's add a small amount of water to this and see if it dissolves in water. Let's add a little bit more water. What do you notice? Do you see formation of a solution? You observe that the benzoic acid is not dissolving in water. No matter how much water we keep on adding, you will observe benzoic acid solid does not dissolve in water. This is because benzoic acid is insoluble in water. Benzoic acid contains a benzene ring, and thereby it has higher number of carbons that will not allow the acid to dissolve in water. The acid group, however, contains a dipole bond as well as a hydrogen bond forming OH group. However, these two groups alone will not be sufficient enough to make benzoic acid soluble in water. What you observe here in this experiment is that benzoic acid is insoluble in water. So in this part of our practical, we observed short chain carboxylic acids are soluble in water. However, long chain carboxylic acids or carboxylic acids with a higher number of carbon atoms in them do not dissolve in water. For example, methanoic and ethanoic acids dissolve well in water. However, benzoic acid did not dissolve in water at all. Benzoic acid or carboxylic acids with high number of carbon atoms in them do not dissolve in water. However, if you take an organic solvent, a non-polar organic solvent, they will dissolve in non-polar organic solvent, as these carboxylic acids are mainly non-polar when their carbon number is higher. The shorter chain carboxylic acids tend to dissolve well in water. However, the long chain carboxylic acids will dissolve well in non-polar solvents. To test this, let's dissolve a small amount of benzoic acid in carbon tetrachloride. We have our CCl4 solution here. Let's take a boiling tube for this, and we'll first take a small amount of benzoic acid into our boiling tube. And then we'll take our carbon tetrachloride and add a few milliliters of carbon tetrachloride into these benzoic acid crystals. As you can see, when I slowly add carbon tetrachloride, the benzoic acid that we had here in the boiling tube started to dissolve. Let's add a little bit more CCl4. You can now very clearly see the white crystals we had here when we transferred benzoic acid into this boiling tube have now disappeared. This is because benzoic acid, although it is insoluble in water, which is a polar solvent, it is soluble in non-polar solvents such as carbon tetrachloride. Let's move on to our summary. We saw that short chain carboxylic acids were soluble in water. Short chain carboxylic acids have small amount of carbon atoms in them. So the short chain carboxylic acid we noticed were soluble in water without any issue. However, when we looked at benzoic acid, which had a greater number of carbon atoms in the molecule, did not dissolve well in the polar solvent water. However, when we dissolved benzoic acid in carbon tetrachloride, we saw that all of the benzoic acid crystals we have taken into this boiling tube dissolved well with carbon tetrachloride, indicating that it is soluble in nonpolar solvents. Now, let's move on to the next part of our practical. In this part of our practical, we are going to observe how these carboxylic acids react with aqueous sodium hydroxide. We have our methanoic, ethanoic and benzoic acids, and we will be reacting these acids with sodium hydroxide. Let's take our test tube labeled methanoic acid, and to that we will be adding methanoic acid, a small amount of methanoic acid, and then we will add sodium hydroxide. Upon addition of sodium hydroxide, you will see we did not observe a layer separation. We saw in the earlier part of this experiment as well, aqueous solutions or water, we saw in our previous experiment as well that methanoic acid dissolves well in water, but in this case we have sodium hydroxide in aqueous medium. You can feel the test tube warming up a little bit. This is due to the reaction of methanoic acid with sodium hydroxide having a neutralization reaction happening. H plus produced from methanoic acid reacts with OH minus from sodium hydroxide and produces water. So due to this neutralization reaction, you can feel that the test tube is warming up a little bit. Now, let's move on to ethanoic acid. We'll take a small amount of ethanoic acid into our test tube labeled ethanoic acid. And to this, let's add a small amount of sodium hydroxide. Just like in the previous experiment, we do not see a layer separation, and we knew that ethanoic acid dissolves well in water. However, in this experiment also, you feel the test tube warming up a little bit because ethanoic acid is an acid, and H pluses released from ethanoic acid reacts with the sodium hydroxide or the OH minuses from the sodium hydroxide and carries out a neutralization reaction. And this is an exothermic reaction, so therefore you can feel that this test tube is warming up a little bit. Now we move on to benzoic acid. We saw in the previous experiments that benzoic acid does not dissolve well in water. Now what we have here is an aqueous solution of sodium hydroxide. Let's see how it reacts with an aqueous solution of sodium hydroxide. Let's take a new test tube and let's add a small amount of benzoic acid. You have here a small quantity of benzoic acid taken into this test tube. And now, let's add a small amount of sodium hydroxide. If you remember, when water was added to benzoic acid in the previous experiment, it did not dissolve at all. It appeared to be hydrophobic. However, when we are adding an aqueous medium of sodium hydroxide, so in this aqueous medium of sodium hydroxide, majority of what you have here is water. However, you can see the benzoic acid seemed to have dissolved completely in this sodium hydroxide. Why might this be? The reason for this is benzoic acid reacts with sodium hydroxide and conducts an acid-base reaction. This acid-base reaction produces sodium benzoate, which is an ionic compound that dissolves in water. So the benzoate, an ion, dissolves well with water, producing a clear solution. There is no layer separation, there is no precipitate formed here because benzoic acid, when reacted with sodium hydroxide, produces a salt that is soluble in water, sodium benzoate. Now, let's move on to the next part of our experiment. Now, let's take a look at how these acids react with sodium carbonate. We have our test tubes labeled methanoic acid, ethanoic acid, and benzoic acid. To these test tubes, let's take a test tube. Now, this is a test tube we are going to test methanoic acid with. So, to that test tube, let's add a small amount of sodium carbonate. And now, to this test tube, let's add a few drops of methanoic acid. Please observe what happens. As you can see, as soon as methanoic acid is added, you can see the formation of bubbles. This formation of bubbles that you observed upon addition of methanoic acid to sodium carbonate is due to the reaction between sodium carbonate and the methanoic acid. Sodium carbonate has a carbonate anion that will receive H plus ions and will turn into carbon dioxide and water. And the bubbles you saw here were carbon dioxide bubbles. Now, let's move on to ethanoic acid. To this test tube, let's take a small quantity of sodium carbonate. And now, to this test tube, let's add a small amount of ethanoic acid. We have here our ethanoic acid. So let's add a small amount of ethanoic acid and observe. We can see here, upon addition of ethanoic acid to sodium carbonate, we see formation of bubbles, or in other words, evolution
of a gas. The reason behind the observation here, or evolution of a gas, is because the carbonate anion again reacts with the H plus that is released by the ethanoic acid. Ethanoic acid is acting as an acid and releasing H plus, and this H plus will react with the carbonate anion and will produce carbon dioxide gas and water. And the gas that you saw released from this reaction mixture was carbon dioxide. And by now, we come to the understanding that carboxylic acid has enough acidity to react with carbonates. You might have learned in the previous parts of organic compounds that alcohols and phenols, although they react with sodium hydroxide, they were never strong enough to show a reaction with carbonates or bicarbonates. Alcohols and phenols both did not show a reaction with carbonates or bicarbonates. However, carboxylic acids show a reaction with carbonates and bicarbonates. Now, let's take a look at benzoic acid. So let's take a test tube and take a small amount of benzoic acid into our test tube. So we have here benzoic acid crystals in this test tube. So we saw earlier when we added water to benzoic acid, it did not dissolve. What we have here is a sodium carbonate solution. It is also an aqueous solution of sodium carbonate. Ideally, since the medium is aqueous, they should not dissolve. However, if benzoic acid reacts with sodium carbonate, it will dissolve and result in a reaction. In the previous two experiments, we saw that the carboxylic acids react really well with carbonates and produce gas, especially and produce carbon dioxide gas. Carbonate, when reacting with H plus ions, will produce carbon dioxide and water. Let's see if we can get the same observation here when benzoic acid is reacted with sodium carbonate. We'll take a small amount of sodium carbonate and add it to our benzoic acid, and we'll mix it. You can see the formation of effervescence. Take a look at this. We can see the formation of bubbles. Now this is due to the formation of carbon dioxide. The bubbles that are formed here is rising through the test tube because of the reaction between sodium carbonate and benzoic acid. Just like in the previous two carboxylic acid that we observed, carbon dioxide gas is released. So that means benzoic acid also reacts really well with sodium carbonate. Benzoic acid releases H pluses that reacts with the carbonate anion and produces carbon dioxide and water. Now, let's move on to our summary. We took small amounts of sodium carbonate into each of these test tubes, and we reacted a small amount of methanoic acid with sodium carbonate. We saw the release of carbon dioxide gas, or we saw the release of a gas, which we happen to know is, we saw the release of a gas. The gas that was released was carbon dioxide. Then we took a look at ethanoic acid. We took small amount of sodium carbonate into this test tube and added with ethanoic acid. And we saw the formation of bubbles, or we saw the release of a gas, and we identified that the gas that is released is carbon dioxide. And finally, we took benzoic acid and reacted with sodium carbonate and saw the release of a gas in that acid as well when reacted with sodium carbonate. So this brings us to the conclusion that the carboxylic acids react well with sodium carbonate, releasing carbon dioxide. Now, let's move on to the next part of our experiment. In this part of our practical, we will be looking at how carboxylic acids react with oxidizing agents. We will be using acidified potassium permanganate and acidified potassium dichromate to test this. We have here potassium permanganate and potassium dichromate. Let's take them and add a little bit of acid to acidify them. Let's take a boiling tube and let's take our potassium permanganate solution. Let's dilute this a little bit as it is too concentrated. To see a color change clearly, it is easier if you have a dilute solution of potassium permanganate. Now, let's acidify this potassium permanganate solution with the help of concentrated sulfuric acid. Now, we have prepared acidified potassium permanganate. We will keep it aside. Now, let's take potassium dichromate. As you can see, the potassium dichromate is orange in color. And let's take another boiling tube and take a small amount of potassium dichromate into our boiling tube. We'll try to dilute it a little further as well. And to that as well, let's add a small amount of concentrated sulfuric acid. Now we have prepared both acidified potassium permanganate and acidified potassium dichromate. As you can see, acidified potassium dichromate is orange in color. Acidified potassium permanganate is purple in color. Now, if you observe here, you can see that each of these test tubes are labeled. Right hand corner, you will see the test tube is labeled methanoic acid and then ethanoic acid and benzoic acid. We have a similar set of test tubes over here as well. We will be using one set of these test tubes to test with potassium permanganate. We will be adding acidified potassium permanganate to these three test tubes and we will be adding methanoic acid, ethanoic acid and benzoic acid respectively to these three test tubes. And to these three test tubes, we will be adding potassium dichromate, acidified potassium dichromate and we will be adding methanoic, ethanoic and benzoic acid respectively to these three test tubes as well. And then we will be heating these test tubes in our water bath here to make the reaction happen faster. Let's take small amounts of methanoic acid into the relevant test tubes. The first test tube we have here is the test tube labeled methanoic acid. We will add small amount of methanoic acid into the two test tubes labeled methanoic acid. Now, there are two other test tubes labeled ethanoic acid. Let's add small amount of ethanoic acid to each of these test tubes. We are adding ethanoic acid only to the test tubes labeled ethanoic acid. Let's move it back. And now, to the two test tubes labeled benzoic acid, let's add a small amount of benzoic acid crystals. We have here our benzoic acid crystals. We'll take a small amount of benzoic acid and add it to our test tubes. So you can see, to the test tube labeled benzoic acid, I added a small amount of benzoic acid solid. We have another test tube labeled benzoic acid. Let's add a small amount of benzoic acid to this test tube as well. Let's move on and add our acidified potassium dichromate into each of these test tubes. Now, the very first set of test tubes are going to be reacted with acidified potassium dichromate, which is a purple color solution. Now, let's take our benzoic acid first and add acidified potassium dichromate. And let's mix it really well. As you can see, the benzoic acid did not seem to mix really well with acidified potassium dichromate. This happened earlier also when we were trying to dissolve benzoic acid with water. However, when you had aqueous sodium hydroxide, it dissolved really well. This indicated when a reaction is taking place, benzoic acid dissolves really well even in an aqueous medium due to the reaction that is taking place. However, when you add acidified potassium dichromate, we can very clearly see benzoic acid does not like to dissolve in acidified potassium permanganate. So, in this potassium permanganate, the reason why benzoic acid does not dissolve in acidified potassium permanganate is due to there being no reaction between potassium permanganate and the benzoic acid. Benzoic acid is not oxidized by acidified potassium permanganate. However, to observe if there is a reaction that can happen at a higher temperature, we will place this in a water bath now. Now, let's move on to ethanoic acid. We'll take our ethanoic acid test tube and we will add a little bit of acidified potassium permanganate. As you see, ethanoic acid mixed really well with acidified potassium permanganate. There is no layer separation. However, the color of potassium permanganate did not change. If you observe here, potassium permanganate was purple in color, and ethanoic acid and potassium permanganate mixture is also still purple in color. You might see a slight dilution in color. That is due to dilution of the solution with ethanoic acid. Again, to see if there is a reaction happening at a higher temperature, let's place this in a water bath. Now, let's move on to methanoic acid. We have here our methanoic acid sample, and let's add a small amount of acidified potassium permanganate to this methanoic acid. As you can see, upon addition of acidified potassium permanganate to methanoic acid, the color of the potassium permanganate is starting to decrease. Let's compare the initial color and the color that we are observing right now. While we wait, we can see the color of potassium permanganate is starting to disappear. This is because formic acid or methanoic acid reacts with acidified potassium permanganate and can oxidize to carbon dioxide and water. So, formic acid or methanoic acid is reacting with acidified potassium permanganate, which is an oxidizing agent, and the methanoic acid is oxidizing into carbon dioxide and water. Now you can see the color of the solution completely disappears. Started off with a purple color, very clear purple color. Now the solution is almost colorless. Let's place this also in a water bath to see if we can obtain a perfectly colorless solution. Now, let's take a look at the samples that we placed in the water bath a while ago. Let's see if the colors have changed any further of the samples we placed in the water bath. We placed our benzoic acid sample in a water bath. We reacted benzoic acid with acidified potassium permanganate, but as you can see, the color of potassium permanganate has not changed. As you can see, the color of potassium permanganate has not changed. It is still persistent. The purple color is still present here. Now, let's move on to the sample where we added ethanoic acid to acidified potassium permanganate. As you can see, ethanoic acid also did not react with acidified potassium permanganate. The color of potassium permanganate persists in this sample as well. The purple color of potassium permanganate is still present, indicating ethanoic acid did not react with potassium permanganate. This means both the benzoic acid and ethanoic acid could not be further oxidized with the use of acidified potassium permanganate. Let's move on to our final sample. We took methanoic acid and reacted with acidified potassium permanganate. We saw even at room temperature, the color of acidified potassium permanganate was starting to disappear. For obtaining a clear solution, we placed it in a water bath, and as you can see, it is completely colorless now as potassium permanganate has oxidized methanoic acid completely, and the permanganate anion has now turned into Mn2+, which is colorless. So the purple color permanganate anion is now present here as Mn2+, which is considered to be colorless. These are the results when these three acids are reacted with acidified potassium permanganate. Now let's move on to acidified potassium dichromate. Let's take our benzoic acid sample and add a small amount of acidified potassium dichromate to our benzoic acid sample. As you can see, the dichromate solution is orange in color. Let's add a small amount of a dichromate solution. We have added a small amount of acidified potassium dichromate. As you can see, we do not observe the color of dichromate reducing, but let's mix these two together and observe if benzoic acid mixed really well or has any reaction between or indicates the presence of any reaction between acidified potassium dichromate and benzoic acid. As you try to mix it, one thing that is very clear to us is that benzoic acid does not mix well with a solution of acidified potassium dichromate. Again, this is due to benzoic acid not having a reaction with acidified potassium dichromate. However, let's leave it aside for a while. And now, let's move on to ethanoic acid. We have our sample of ethanoic acid here. Let's add acidified potassium dichromate to this ethanoic acid sample. As you can see, the color of acidified potassium dichromate is still persistent here. This indicates at room temperature, ethanoic acid does not react with acidified potassium dichromate. Let's leave it aside for a while as well. And now, let's finally take methanoic acid. We have our sample of methanoic acid here, and to this sample, let's add a small amount of acidified potassium dichromate. Please observe the color change. As you can see, when you add acidified potassium dichromate, the color of potassium dichromate is seemingly still persistent. This is because the oxidation of methanoic acid is happening very slowly and the dichromate ions are being used up very slowly. However, the color is slowly starting to decrease. If you observe the sample where we added acidified potassium dichromate to ethanoic acid, you can start to see a clear difference. Now let's mix it really well. You can see the color is no longer appearing to be orange. It is leaning more towards green. To see a bit more clearer color change, let's place all of these three samples that were treated with potassium dichromate in a water bath for a while. We have our benzoic acid and acidified potassium dichromate reaction mixture. We have our ethanoic acid and acidified potassium dichromate reaction mixture. And finally, we can already see a faint green color in methanoic acid reacted with acidified potassium dichromate mixture. Let's place it in a water bath as well. Let's heat it for a while and we'll come back and take a look at the observations. Now, let's take the first sample where we reacted methanoic acid with acidified potassium dichromate, and you can see the sample has turned green. This is because methanoic acid reacts with acidified potassium dichromate and gets oxidized and turns into carbon dioxide and water. In that process, the dichromate ions turns into chromium 3+. Dichromate ions are orange in color, chromium 3+ ions are green in color. So you will observe the final solution to be a green color solution. Now, let's take a look at the other two samples. We took our ethanoic acid solution, or we took our ethanoic acid and reacted it with acidified potassium dichromate, and even after leaving it in a water bath for over 5 minutes, you can see the color of the solution has not changed. This indicates that ethanoic acid will not get further oxidized with potassium dichromate. Now we have a benzoic acid and potassium dichromate mixture. So as you can see, when you added benzoic acid to acidified potassium dichromate, we did not observe a color change, and even after leaving it in a water bath for a very long time, we did not see any reaction taking place between acidified potassium dichromate and benzoic acid. So therefore, acidified potassium dichromate does not react with benzoic acid, or benzoic acid does not get oxidized by acidified potassium dichromate. Let's take a look at the summary of this part of the practical. We tried to oxidize the carboxylic acid we had in front of us, and out of the 3 carboxylic acid, only methanoic acid underwent oxidation with both acidified potassium dichromate and acidified potassium permanganate. In the case of acidified potassium permanganate, we saw the color of the permanganate ion completely disappeared, giving us a colorless solution. This indicated that the formic acid or methanoic acid completely got oxidized into carbon dioxide and water. A similar observation was observed when it comes to methanoic acid reacting with acidified potassium dichromate. Dichromate, which was orange in color, turned into a green color solution because dichromate ion, which is orange in color, underwent reduction and turned into a chromium 3+ ions, which is a green color solution. Dichromate ions underwent a reduction because the formic acid or methanoic acid got oxidized into carbon dioxide and water. The other two acids did not indicate any signs of oxidation when reacted with acidified potassium dichromate or acidified potassium permanganate. They do not show us any signs of oxidation with either of these oxidizing agents because these two acids cannot get oxidized any further. Now, let's move on to the next part of our experiment. In this part of our experiment, we will be forming esters by reacting these carboxylic acids with alcohol, and we'll be using concentrated sulfuric acid as a catalyst. So we have methanoic acid, ethanoic acid and benzoic acid. We'll be adding ethanol to each of these test tubes along with concentrated sulfuric acid, and then we'll be warming this mixture in a water bath, allowing the reaction to happen at a higher pace. And then we will be neutralizing the solutions with the help of 5% sodium bicarbonate solution, and we will be observing the smell that is given off by the esters that are produced. Now, let's move on to our experiment. Let's take our test tube labeled methanoic acid, and to this test tube, let's add some methanoic acid. We will add about 1 cubic centimeters of methanoic acid into this test tube. And now let's add a small amount of ethanol. Let's open the bottle of ethanol. And take a small amount of ethanol into our test tube. Now, into this test tube, let's add our catalyst, which is concentrated sulfuric acid. We have here our concentrated sulfuric acid. Be very careful when handling concentrated sulfuric acid because it's really corrosive. Make sure to not get it on your skin. I have added a few drops of concentrated sulfuric acid. Now, let's mix it really well and let's place it in a water bath. We have to gently heat it for about 1 minute, and after that, we will observe the smell that it produces. Now, we are placing it in a water bath, and while it waits in a water bath, to these 3 petri dishes that I have in front of me, I will be adding 5% sodium bicarbonate solution. We have here a solution of sodium bicarbonate that we have prepared earlier, a 5% sodium bicarbonate solution. We'll be adding small amounts of sodium bicarbonate into these 3 petri dishes. Carboxylic acids do not necessarily smell really good. However, when it comes to formation of esters, esters have a very pleasant smell for the most part. So the esters that we are producing today also have very pleasant smells. Now, we have left this reaction mixture in the water bath for a while now. Let's take this and transfer this solution into our sodium bicarbonate solution in a petri dish and observe the smell. When you smell the ester, the smell that you get is characteristic smell of rum. What you form here as an ester is ethyl methanoate ester, has the characteristic smell of rum. Now, let's move on to ethanoic acid. We'll take the test tube labeled ethanoic acid and let's add around 1 cubic centimeter of ethanoic acid into this test tube. And just like in the previous experiment, we will add small amount of ethanol into this test tube as well. Finally, let's add few drops of concentrated sulfuric acid. We have added sulfuric acid to an ethanoic acid and ethanol mixture. Now let's mix it really well. After mixing it really well, let's place it in a water bath and heat it gently for about a minute. We have waited for a minute now. Let's take our reaction mixture and pour this out onto 5% sodium bicarbonate solution that we have here. This, what you form here, is ethyl ethanoate. And the ethyl ethanoate ester has a very pleasant, fruity smell. So, if you are ever in a lab, if you can get your hands on these chemicals, try to kind of produce these esters and observe the smells. As you can see, we cannot give you the experience of smell through media yet, so you would not observe these smells, but I can communicate to you what it smells like. Ethyl ethanoate ester that is produced here has a very pleasant, fruity smell. Now, let's move on to our final acid, which is the benzoic acid. We have here a test tube labeled benzoic acid. Let's take our benzoic acid solid that we have over here and add a small amount of benzoic acid into our test tube. To this benzoic acid, let's add a small amount of alcohol or ethanol. As you can see, the benzoic acid dissolved in ethanol, an organic solvent. And now, to this ethanol benzoic acid mixture, let's add a small amount of concentrated sulfuric acid. I have added a few drops of concentrated sulfuric acid here. Now, let's place this mixture in a water bath for about 1 minute. When we react a carboxylic acid and an alcohol together in the presence of concentrated sulfuric acid, we allow an esterification reaction to happen. In this case, we took benzoic acid, reacted with ethyl alcohol, and the result would be ethyl benzoate ester. Now, after leaving it for about a minute, let's observe the smell of the ethyl benzoate ester. Now, let's take this benzoic acid, ethanol and sulfuric acid mixture. Now, it has reacted and formed ethyl benzoate ester. Let's transfer this mixture into 5% sodium bicarbonate solution and observe the smell. Ethyl benzoate that is formed here smells of menthol. You have a very pleasant menthol smell coming out of this ethyl benzoate ester. Like I mentioned earlier, since you cannot observe these smells, if you ever get a chance, try to do these reactions and observe these smells for yourself as well. Now, let's take a look at the summary. We reacted methanoic acid with ethanol in the presence of sulfuric acid and produced ethyl methanoate ester. This ester had the characteristic smell of rum. Then we reacted ethanoic acid with ethyl alcohol in the presence of sulfuric acid and we produced ethyl ethanoate ester, which had a very pleasant fruity smell. And finally, we reacted benzoic acid with ethanol in the presence of sulfuric acid and produced ethyl benzoate ester, which had a smell of menthol. Now, let's move on to the next part of our practical. In this part of our practical, we are going to see how these carboxylic acids react with the tolerance reagent. Now, before we move on with the practical, we need to first prepare the tolerance reagent. Tolerance reagent is also referred to as ammoniacal silver nitrate. Normally, when we are conducting a test with tolerance reagent, we have to freshly prepare the tolerance reagent. So, let's go ahead and prepare our tolerance reagent. For that, we will be needing silver nitrate. We'll take a boiling tube and add a small amount of silver nitrate. To this silver nitrate solution, we'll be adding a small amount of sodium hydroxide. We have here our sodium hydroxide. Let's add a small drop of sodium hydroxide to produce this brown color precipitate. And now we are going to add concentrated ammonia until this suspension turns colorless. We have here our concentrated ammonia solution. Let's add our concentrated ammonia solution drop by drop until all of the precipitate completely disappears. As you can see, the precipitate is disappearing. There's still a little bit more. We'll add a little bit more ammonia until all of the precipitate is completely dissolved. Now, as you can see, we have prepared a tolerance reagent, which is ammoniacal silver nitrate, and you do not see the brown color precipitate persisting in this mixture, and we have successfully prepared our tolerance reagent. Now, let's take our test tubes that are labeled and add small amounts of methanoic acid, ethanoic acid, and benzoic acid into each of these test tubes. We have here our first test tube, which is labeled methanoic acid. Let's take around 1 cubic centimeter of methanoic acid into our test tube labeled methanoic acid. And then we have our test tube labeled ethanoic acid. To that, we'll add around 1 cubic centimeter of ethanoic acid. And finally, we have our test tube labeled benzoic acid. To that, we will take our benzoic acid crystals and add a small amount of benzoic acid into this test tube. As you can see, in this test tube we have our benzoic acid. Now, to each of these test tubes, let's add our tolerance reagent and gently warm it to see what the results are. We have our tolerance reagent here. Let's add a small amount of tolerance reagent into our methanoic acid. As you can see, when the two reactants are mixed, we can see formation of a white color smoke. And now we will be placing this mixture in our water bath. Now we have left the reaction mixture in the water bath for a while. In this test tube we had methanoic acid treated with tolerance reagent, and we have heated it for a while now. Let's take the test tube out and observe what changes have taken place. When you take the test tube out, you can observe the inner walls of the test tube is coated with silver, creating a silver mirror. Let's remove the contents of this test tube. After removing the contents of the test tube, we can very clearly see the silver color of the test tube here. We say a silver mirror has been formed. A positive test for tolerance reagent, which is the formation of a silver mirror, is only given when whatever that is treated with tolerance reagent can undergo oxidation. This means the formic acid that was reacted with tolerance reagent, or in other words, the methanoic acid that was reacted with tolerance reagent underwent oxidation. Therefore, the silver plus ions in tolerance reagent underwent a reduction. This produced silver solid. This silver solid got coated in the interior walls of the test tube, producing a silver mirror. So what you see here is the positive test result of the tolerance reagent test, which indicates the methanoic acid underwent oxidation. However, the other two acids, the benzoic acid and our ethanoic acid that we have here, do not get oxidized. We have seen this in previous experiments where we used oxidizing agents such as potassium permanganate or acidified potassium dichromate. We saw that ethanoic acid and benzoic acid does not undergo any oxidation. It will be similar with tolerance reagent, as tolerance reagent is not an extremely good oxidizing agent. It will also not be able to oxidize ethanoic acid or benzoic acid. But let's carry out this practical and see if we can get a silver mirror with the tolerance reagent when reacted with ethanoic acid or benzoic acid. We have our tolerance reagent here. Let's add a small amount of tolerance reagent into our ethanoic acid sample, and we have our benzoic acid here. Let's add our tolerance reagent to our benzoic acid sample as well. As you can see, it did not readily dissolve the benzoic acid, but let's shake it for a while and see if we can dissolve some benzoic acid in our tolerance reagent. You can see some benzoic acid dissolves in the tolerance reagent, but still there's a lot of it that did not dissolve. However, let's place both of these test tubes in a water bath and see if we can observe the formation of a silver mirror. In both of these test tubes, we have a carboxylic acid mixed with tolerance reagent. In test tube number 1, we have ethanoic acid mixed with tolerance reagent, and in the second test tube, we have benzoic acid mixed with tolerance reagent. Let's place them both in a water bath and wait for a little while to see if we see a formation of a silver mirror. It has been a while now. We have placed the benzoic acid and the ethanoic acid reacted with tolerance reagent in a water bath for several minutes now. Let's take these test tubes out of the water bath. As you can see, in both of these test tubes, we do not observe a positive result for the test with tolerance reagent. We do not observe the formation of a silver mirror when we reacted ethanoic acid with tolerance reagent, or we do not see a positive result when we reacted benzoic acid with tolerance reagent as well. This indicates that tolerance reagent will not oxidize ethanoic acid or benzoic acid. In summary, we took tolerance reagent and we reacted methanoic acid, ethanoic acid and benzoic acid, and we observed the changes that take place. And we noticed methanoic acid reacted well with tolerance reagent and got oxidized and produced a silver mirror. The reason for the formation of silver mirror, as I explained earlier, was due to the reduction of silver ions in tolerance reagent to silver plus, as well as oxidation that takes place in methanoic acid to carbon dioxide and water. Ethanoic acid, when reacted with Tollens reagent, did not show us a reaction. Ethanoic acid cannot oxidize any further in the presence of Tollens reagent, so therefore we did not observe the formation of a silver mirror. Benzoic acid also had the same outcome. Benzoic acid, when reacted with Tollens reagent, do not show us a reaction as it cannot oxidize further with the use of Tollens reagent. With that, we conclude this practical, and let's move on to the next session where we will be talking about important points related to this practical and questions revolving around this practical.
Students, we had a look at the theory parts revolving around carboxylic acids or properties of carboxylic acids. Then we went into the lab, conducted our experiment, and now we are here to talk about some questions revolving around carboxylic acids. So let's move on to the first question. Consider the series of reactions below and answer the questions that is given below. So we have a reaction that we are given here. We have EFGH finally forming this compound. They are asking us to identify what EFG and H are and draw their structures. Apart from that, they ask us to identify the reagents L and M and draw their structures as well. So before we move on to actually answering this question, we'll identify this compound or we actually can draw this compound again so that we can identify what we need to do to answer the two questions given here. Always when you have a question like this, it's easier when you can first of all draw this structure separately to observe it a little bit better. We'll move this a little bit up like this. So we have CH3, CH, double bonded to CH, CH2, and then we have an O, C, O, CH3. Now we have a clear idea of the compound that we are dealing with. What we have here is an ester. So this indicates that when it comes to an ester like this one especially, we can actually figure out where the ester bond is. So if you take a look at this region, this is where the ester bond is, and towards our right hand side we have our carboxylic acid. And towards your left hand side, this section would have come from an alcohol. So now we need to identify what each of these compounds are. So carboxylic acid would have been, it's very easy. You can actually think of what the carboxylic acid is. If this is the remaining part of the carboxylic acid, because as you know, a ester bond is formed when a carboxylic acid reacts with an alcohol or an acyl chloride reacts with an alcohol. So if you are operating under the assumption that this is a carboxylic acid, if this is the remaining part of the carboxylic acid, we can very clearly identify the carboxylic acid that we are dealing with here is acetic acid. And then we can move on to the alcohol. So the alcohol that we have here is CH3, CH, and then there's a double bond, a CH, and CH2OH. So this is our alcohol. This is the alcohol that we have obtained, and you can see there's a double bond in the middle between the second and the third carbon. So to go any further, we actually need more information. So let's go back to the question here again. Let's go back to our question. So in this question they say, first we have something called E, and when it's reacting with the reagent L, you're producing F. Now soon after we reacted with L and when we produce F, we have heated it, and heating it alone has produced G. Just heat, nothing else is given for us to even figure out, meaning just heating it has produced G. So now you have to think of reactions that are going to produce a product, and when the product itself is heated, another product is going to be produced. So is there any reaction that you can think of like that? So until we move on to this part, you can keep thinking about that. And then you can see the produced product G, when added with lithium aluminium hydride, has produced H. Now we know what H is, because we know when you take this final compound that we have formed here, it is an ester formed by reacting a carboxylic acid with an alcohol. So H is going to be our alcohol and M is going to be our carboxylic acid, because normally carboxylic acid is added alongside concentrated sulfuric acid. So that's why we have carboxylic acid slash H3O plus. So we have the carboxylic acid M reacting with H, which is our alcohol. The structure of the alcohol was drawn a little while ago. So H and M are already identified, but we need to identify G, F, and E. So what is the reaction that when you add, let's say, when you add a reagent like L, and when you allow the reaction to take place, and the product that is produced, when it is directly heated, you form a completely different product. What type of reaction does this? If you're thinking about aldol condensation, you will be right. If you're thinking about aldol condensation, you will be right. So there are 4 carbons here. That means if you are going to get to that point with the use of aldol condensation, we can actually take acetaldehyde. If you take acetaldehyde and react it with dilute sodium hydroxide, the alpha carbon or hydrogen in the alpha carbon will get removed, forming a nucleophile. So I can indicate that over here. Now students, this produces a nucleophile. If I draw the nucleophile over here, you can see it's going to produce this nucleophile CH2, C double bonded oxygen and hydrogen, and we have a lone pair of electrons here, which makes it a nucleophile. And as you know, when it comes to this aldehyde, we are going to have a partially negative oxygen and a partially positive carbon atom. So this carbon atom is susceptible to an attack from a nucleophile like this. At that point, this oxygen carbon bond will break, and you'll be forming this compound CH3 CO minus. I can say this ion is formed H, or else we can write this group over here CH2 COH, and we can have a proton take these lone pair of electrons to form an OH group there. So finally you'll be producing an OH here. I will skip writing that additional step. We can straight away get to this point. So now students, after aldol condensation is done, if you heat this product, you can get a double bond between the second and the third carbon. So when you heat this product, you get to this product that I'm just writing down here. So now we have found an answer to what type of reaction that normally takes place when you add a reagent to form a product, and when the product is heated, if you get a double bond, then we know, or if you get a separate product, then you know we're talking about aldol condensation. Or aldol condensation is one of the reactions that takes place like that. So now we have gotten to this point, and then we saw in the next step they added lithium aluminium hydride. So when it comes to an aldehyde, if you react an aldehyde with lithium aluminium hydride, what happens when you react an aldehyde with lithium aluminium hydride? What takes place? It will get reduced. The aldehyde group will reduce to form a alcohol group. So CH3, CH, and the double bond, you have a CH, CH2, OH. The aldehyde group got reduced to form the alcohol group. And now, if this alcohol is reacted with a carboxylic acid, you will form the ester. So the carboxylic acid we saw earlier onwards, the carboxylic acid that we obtained through our findings was acetic acid. So now all parts of this question is properly answered. So let's move on to the answer. We can start writing the answer on the next slide. So we will write down the answer here. We had the starting compound CH3, C, double bonded O and H. This is our E. And then we reacted E. With dilute sodium hydroxide, producing this compound CH3 COH CH2 C double bonded OH. This compound is our F compound. And then we took our F compound and we heated it. We heated the F compound. So by heating the F compound, we got to form a double bond between the second and the third carbon, and the aldehyde group did not get changed. Then after that, after we obtained the aldehyde group, we added lithium, aluminium hydride, which converted the aldehyde group into a alcohol group. We write that answer here: CH3, CH, CH, CH2, OH. Now, after forming this particular alcohol, which is our H, so I forgot to mention earlier, after forming F, what we have here is the G compound. This is our G compound. And then we have our H compound formed here. We have our H compound formed here. And then, if you take the H compound and react it with acetic acid, CH3, C double bond OOH, along with H3O plus, we get to our final product. This is our final product. So you can see this is the final product that we will form. And in the question they asked what was the reagent that was added before forming this final product. So they are asking what this particular reagent is. So they have given it a name. We call this M in the question. So M is acetic acid. And then they wanted to know what the reagent was when we were converting the initial organic compound into F. So this is going to be L. The question asked what the initial reagent that we used for the conversion of E to F was, and that was denoted by the letter L. So letter L, the answer for L is sodium hydroxide. Answer for L is sodium hydroxide. So this is the reaction. This is the reaction that takes place. You have acetaldehyde or ethanol turning into an aldehyde, or we conduct aldehyde condensation, and after heating it we can get a double bond between the second and the third carbon. And as you reacted with lithium aluminum hydride, which is a reducing agent, we reduce the aldehyde group to form an alcohol, and that alcohol was reacted with a carboxylic acid to obtain our final product. Now let's move on to this question again and see if we answered all the parts. Identify E, F, G and H, which we did. We drew their structures as well. Identify L and M and draw their structures, which we did. We identify that L is sodium hydroxide and M is acetic acid. Now, let's move on to our next question. In this question, consider the compounds below and choose the true statement about these compounds. So they're asking what out of these statements are true or is true. There might be only one statement. So we have phenol, we have carboxylic acid, and we have a primary alcohol. Now students, this would be a good time for you to remember the acidity of each of these compounds when it comes to alcohols, phenols, and carboxylic acids. How they react with different compounds should be kept in mind when it comes to answering a question like this. As you know, alcohols are the least acidic. So we'll arrange them according to our knowledge about the acidity, or about our knowledge regarding the acidic properties. So we have CH2, OH, and then we have phenols. We know phenols are more acidic compared to alcohols, especially primary alcohols. And then we have carboxylic acids. Carboxylic acids are the most acidic out of the lot here. Right. So now let's take a look at the different types of reagents that these three would react with. You know, when it comes to alcohols, it will react with sodium, forming sodium alkoxides. For example, this one would form the following compound: CH2O minus and Na plus, along with hydrogen gas. When it comes to phenols also, we'll form sodium phenoxide, O minus and Na plus, forming a colorless, odorless gas, which is hydrogen. When it comes to carboxylic acid, we have benzoic acid here. We'll be forming sodium benzoate and hydrogen gas. Sodium benzoate and hydrogen gas. And if you react this with, also you will see a few observations. If you react this with sodium hydroxide, so when it comes to sodium hydroxide, we know when it comes to alcohols, such as primary alcohols like the first one that is given here, alcohols do not react with sodium hydroxide, no reaction there. When it comes to phenols, of course, they would react with sodium hydroxide to form sodium phenoxide or sodium phenolate and water. When it comes to carboxylic acids, of course, they will also react easily with sodium hydroxide to form, in this case we have benzoic acid, will form sodium benzoate along with water. Then we normally look at the reaction between sodium carbonate and sodium carbonate. Sodium carbonate or sodium bicarbonate, both can be used for this experiment. When it comes to primary alcohols, they will not react with sodium carbonate or sodium bicarbonate. When it comes to phenols, phenols are also not strong enough to react with sodium carbonate or sodium bicarbonate. But carboxylic acids can react with sodium carbonate and also sodium bicarbonate. So again, we will be forming sodium benzoate alongside carbon dioxide and water. Now, the reason behind the carbonate ion got converted into carbon dioxide and water is because in the presence of the carboxylic acid, carbonate ion
was displaced as carboxylic, or was displaced as carbonic acid in the presence of this carboxylic acid, which is benzoic acid. In the presence of benzoic acid, carbonate ion got displaced as carbonic acid. And carbonic acid is not very stable, so it breaks down into carbon dioxide and water. But the main important point here is that carboxylic acids were strong enough to displace the carbonic acid when it was present as the carbonate ion. If you quickly jot down that reaction, CO3 2 minus, 2H pluses will form, this is a reversible reaction, but in this case we have formed carbonic acid and it has gotten broken down into H2O and carbon dioxide. Now students, the only reason that the carbonate ion was displaced as carbonic acid was because the carbonic acid was weaker compared to the carboxylic acid. So carboxylic acids, or in this case what we have here is benzoic acid as our carboxylic acid. So I will write the benzoic acid. Benzoic acid, or any other carboxylic acid for that matter, has a higher acidity than carbonic acid. But we saw phenols were not able to react with the carbonic acid, or it was not able to displace the carbonic acid. With the carbonates, we didn't see any reaction when it comes to phenols, indicating the acidity of phenols is lower than acidity of phenols are lower than carbonic acids. So students, again, this is just a reminder of what type of reactions are normally taking place when you are reacting different types of compounds like sodium hydroxide and sodium carbonate with these acidic organic compounds, primary alcohols, phenols and carboxylic acids. Primary alcohols react with metallic sodium but does not show a reaction with sodium hydroxide or sodium carbonate. Phenol shows a reaction with metallic sodium as well as sodium hydroxide, but it does not react with sodium carbonate. Carboxylic acid, in this case benzoic acid, will react with all three of metallic sodium, sodium hydroxide and sodium carbonate. So with this information now, let's move on to the question. The first answer that they have given, they're asking us to figure out what are the correct answers. First answer is, when added with sodium hydroxide, only A and B will react to form their corresponding sodium salt. Only A and B. Interesting point. Only A and B. So what is A and B? A is phenol, B is carboxylic acid. Yes, with sodium hydroxide, only A and B can react. We saw primary alcohols are capable of only reacting with metallic sodium. So this cannot react with sodium hydroxide. So the first statement is correct. First statement itself is correct. So the answer would be 1. But let's take a look at the other answers as well. Now the second statement, when added with sodium hydroxide, only B and C will react to form their corresponding sodium salt. B and C. Yes, B does react, but does C react? Does C react? No. So this is incorrect. B can react, C can't react, and plus they say only B and C, of course not. Then when we move on to the third answer, it says, when added with sodium hydroxide, A, B and C will react to form their corresponding sodium salt. A is correct, B is correct, but C is not correct. So therefore, this answer is also incorrect.
Then when added with sodium carbonate, only A and B will react to form their corresponding sodium salt. So when added with sodium carbonate, now we saw sodium carbonate only reacted with the carboxylic acid. So there's only one carboxylic acid here, which is the B answer. Does it react with phenols? No. Sodium carbonate does not show a reaction with phenols. So since they have mentioned A, which is incorrect, you can't take this answer as a correct answer because A is built into the answer. If they only mention only B would react, it would be correct. But since A is also mentioned, you can't take the fourth answer as a correct answer. When added with sodium carbonate, A, B and C will react to form the corresponding sodium salt. Of course not, especially primary alcohols do not react with sodium carbonate at all, and we know phenols also don't react, only B reacts, which is carboxylic acid here. So the answer is definitely incorrect when it comes to the fifth one. So the only correct answer that they have given is 1. So answer number 1 is the only correct answer. All others were incorrect. All others were incorrect. Now let's move on to the next question. In the next question, complete the reaction series below to produce the compound given below. So we have a compound that is given to us here, and they're asking you to complete the reaction series. Include the suitable compounds in the boxes and write the suitable reagents in the circles. So let's take a look at the actual reaction series that they have given here. They have given here reaction series, and we have to write the compounds in the boxes and the reagents in the circles. So let's get started with this. But before we start, like I always tell you, we have to observe the structure over here and develop an idea about what type of reaction would have taken place to produce this final structure we have at hand. So what does this final structure tell you? You can see that there's a COOC type of bond, which is an ester bond. That indicates that this particular bond, if you break it, you can get a corresponding carboxylic acid and an alcohol. So carboxylic acid and alcohol might have joined together to form this final compound that we have here. So this is our carboxylic acid part. And this section was brought in by our alcohol group. Right, so now let's figure out what the alcohol was as well as what the carboxylic acid was. So it's easier to start with the left hand side. So we have an alcohol here. We'll draw the alcohol like this. So CH2OH, CH2OH, and the ortho position is free. On the meta position, we have a Br. And over here, we have the carboxylic acid group. We can see this C double bonded oxygen came from the carboxylic acid group. So we can write the carboxylic acid here, C double bonded OH here. And again, the ortho position is free, and in the meta position we see a Br. Now, after writing these two down, you should have a very clear idea about some sort of relationship between these two
compounds. You can see both of these compounds in their meta position, there's a bromine group. And at the same time, if you think a step further, you can see that there's a alcohol group connected to the benzene ring directly. And if you oxidize this CH or primary alcohol that we have here, you can get to the carboxylic acid easily. So now we actually have an idea about how we might be obtaining this carboxylic acid. So now let's move on to the actual few steps that we have been given here. Now students, when you're trying to carry out this conversion, you have to keep in mind that your Br group is present at a meta location, or it's compared to the carboxylic acid group, it is at a meta position. So you have to be very careful with where you're going to be starting this particular conversion. Again, you can see you need to produce this alcohol, and compared to the alcohol, you have a bromine group in the meta location, and compared to the carboxylic acid group attached to the benzene ring, you have bromine in the meta location. Now let's move on to the answer. Now students, before we start answering the question here, we need to figure out what each of these boxes might contain. Now you can see, finally, we are going to join the carboxylic acid group with the alcohol group to produce this ester. So L and M would definitely mean one of these L or one of these M would mean one is a carboxylic acid, the other one is the primary alcohol. So which one is the going to contain the alcohol? Is it M that is going to contain the alcohol, or is it L that is going to contain the alcohol? So to answer that, take a look at the number of steps that we have here. We can see there are 3 steps producing M, and we have 1, 2, 3, 4 steps producing L. So now we have benzene here. Starting from benzene, we need to produce a carboxylic acid attached to the benzene ring with bromine at meta position, and we need to have the alcohol, primary alcohol, with a bromine group attached to the meta position. Now I told you, by looking at this, you can see you can form the alcohol and then convert it into carboxylic acid by oxidation, or else you can form the carboxylic acid, which can be done much easily compared to forming an alcohol. You can have the carboxylic acid reduced to form the alcohol. So it can be either way. But in this particular reaction, the easiest way to go is attaching a methyl group to this benzene, and then we can move on to attaching a bromine. However, students, you know, methyl groups are ortho-para directing groups. So because of that, if you attach a methyl group to the benzene and then move on to attach a bromine, it will not necessarily work, because the bromine will attach to a ortho or a para position, but we want bromine in a meta position. So after attaching the methyl group, we can convert it into a carboxylic acid group. Now carboxylic acid group is going to be a meta directing group. So because of that, after attaching the methyl group, we can convert it into a carboxylic acid group, and then we can attach the bromine group. So this has 3 steps, right? Methyl group, and then we attach the carboxylic acid, and then to the carboxylic acid containing benzene or benzoic acid, we can add the bromine group. So has 3 steps into when it comes to producing the benzoic acid with bromine at the meta location. So only 3 steps are there on the right hand side of this particular reaction series. So this side will be producing our benzoic acid with bromine at the meta
position. And then that means this side will be producing our primary alcohol. Actually, it will be following the same steps as the right hand side of this reaction series up until this point, where you produce the carboxylic acid with bromine at the meta position. But afterwards, we can actually reduce the carboxylic acid to produce an alcohol. We know lithium aluminum hydride will be able to reduce the carboxylic acid group into an alcohol. So we can do that to produce the alcohol that we need. So students, without further ado, let's fill in these boxes. Let's zoom in so that we can actually fill these boxes in properly. Right, so let's move on to the first step. We have benzene here. Right, benzene can be converted into methylbenzene by adding CH3Cl and anhydrous AlCl3 will be forming methylbenzene. And if you take methylbenzene and react it with acidified potassium permanganate, methylbenzene reacted with acidified potassium permanganate, instead of writing the reagents within the circle, I will write it right next to the circle. Acidified KMNO4 will produce benzoic acid. Now, although methyl groups are ortho-para-directors, carboxylic acid groups are meta-directors. So therefore, now we can use this reaction where you can add bromine, Br2 and AlCl3. Actually, you can use Br2 along with iron powder. It will also go on to produce the product that we want. This is O. You can use either one. Now, you will be producing this compound. COOH, and the ortho and the para positions are going to be free. In one of the meta positions, you will have your Br connected. Now students, on the left hand side of this reaction series, we are going to have the same reactions. We are going to be using Fiedel-Crafts alkylation. CH3Cl and anhydrous aluminum chloride will produce methylbenzene. And if you take the methylbenzene and react with oxidizing agent such as H plus KMNO4, will be forming benzoic acid. And when you take the benzoic acid and react it with Br2 and anhydrous aluminum chloride, you'll be forming your carboxylic acid group attached benzene ring with bromine at the meta location. And this product is the same as what we obtained over here. You can see those two are the same. But one final reagent, lithium aluminium hydride and dry ether, followed by addition of water. We will write that here. We will write the reagents here. Lithium aluminium hydride, dry ether, followed by addition of water, will produce the primary alcohol we wanted. Basically, the carboxylic acid group or carboxyl acid group gets converted into an alcohol group. And when these two are joined together in the presence of concentrated sulfuric acid, you will be forming the ester that is given here. This ester that is given here will be formed when you react these two, alcohol and the carboxylic acid, with concentrated sulfuric acid. So students, this is how you would answer a reaction series like this. And keep in mind, I have written the reagents that should come in circles outside of the circle because I didn't have enough space to write it within the circle, but you also can note what the reagents are because I have written the reagents right next to the circles. Right students, so this is the answer to the question that was asked. Now students, let's take a look at the fourth question. They say an aromatic compound named X containing the molecular formula C9H12O reacts with sodium to produce a colorless, odorless gas. It produces a colorless, odorless gas, and that gas is named Y. And keep in mind, this aromatic compound that contains an oxygen also reacts with sodium. So students, what actually reacts with sodium? We know when it comes to organic substances that have acidic properties tend to react with sodium. So we know a few things that react with sodium. Alcohols, phenols, carboxylic acids react with sodium. All of them contain an O. Actually, carboxylic acid contains two oxygens. So therefore, we can be very clear that this is definitely not a carboxylic acid because it doesn't have two oxygens. It has only one oxygen. So it could be a phenol or an alcohol. However, we can move on to the next step to identify or figure out more details about this particular substance. They say X reacts with concentrated hydrochloric acid and zinc chloride to produce a cloudy precipitate instantly. So what is concentrated hydrochloric acid along with zinc chloride? What is this? This is Lucas reagent. You can say Lucas. Sometimes you pronounce it as Lucas. So we have Lucas reagent here. So Lucas reagent is normally used to identify the presence of a tertiary alcohol. Tertiary alcohol produces a turbidity instantly with Lucas reagent. Normally, secondary alcohols take about 10 minutes to produce a turbidity. Primary alcohols takes even longer to produce a turbidity with Lucas reagent. So let's quickly remind ourselves about Lucas reagent. So students, if you take a tertiary alcohol, such as this tertiary alcohol that I'm writing now, if you react it with Lucas reagent, you'll be forming a tertiary halogenoalkane. You'll be forming a tertiary halogenoalkane. And as you would know, tertiary halogenoalkanes are insoluble in water. This is insoluble in water, forms a turbidity. Instantly. It forms a turbidity instantly. It forms a turbidity instantly because this particular halogenoalkane, tertiary halogenoalkanes that are formed when tertiary alcohols are reacted with Lucas reagent is insoluble in water, and the turbidity is produced instantly. And can we say the same about secondary alcohols? No, secondary alcohols takes about 10 minutes, right? If it's a secondary alcohol, it takes about 10 minutes. And if it's a primary alcohol, it takes even longer. So we can actually use Lucas reagent to identify the presence of a tertiary alcohol. But what about the fact that they say this is an aromatic compound? So can it be phenol? Because you have a OH and this is an aromatic compound, it could be a phenol also. But does phenol react with Lucas? No. Phenols do not show a reaction with Lucas. It does not give a turbidity with Lucas instantly. So therefore, the answer that we are looking for here has to be a tertiary alcohol. So while keeping that in mind, let's answer the first question that they ask us here. Draw the structure of Y in the box given below. So any alcohol, even let's take phenol. If alcohol or phenol, even carboxylic acids, when they react with metallic sodium, what is the odorless, colorless gas that is produced? Hydrogen. So over here, what we have is a hydrogen. So if you're drawing the structure of hydrogen, we can draw it like this. So the gas that is produced is hydrogen, H2. And then they ask you to draw the structure of X in the box given below. So we have already figured out that the compound that we are currently dealing with, X, is going to be a tertiary alcohol. So let's see what tertiary alcohol could be formed with the number of carbon and hydrogen atoms that we are given. They say 9 carbon atoms, 12 hydrogen atoms, and 1 oxygen. So we have phenol. Phenol must be connected to 1 carbon. So this carbon might be connected to the OH, and this carbon should have 2 other alkyl groups as well. So to fulfill that requirement, we can put 1 CH3 here. So now let's take a look at the number of carbons that we have used up. 6 carbons for the benzene ring, 7th carbon here, 8th carbon here. We are left with 1 more carbon. So let's add a CH3 group here as well. Let's see if the number of hydrogens are balanced now. So in the benzene ring, we have 5 hydrogens here, and we have 3 hydrogens each in each of these methyl groups. 5 plus 6 is 11. 11 plus the final hydrogen over here is 12. So altogether, we have 12 hydrogens and only 1 oxygen. So therefore, C9H12O molecular formula is satisfied. So this is the compound, or this is the aromatic compound X we were talking about. This will react with metallic sodium, as well as this will produce a turbidity when you are reacting this with Lucas reagent. Let's move on to the next question.
when we have salicylic acid here is added with an aqueous solution of sodium carbonate, what can be produced? So students, we know very well when it comes to sodium carbonate, does sodium carbonate react with phenol? If you take phenol and react phenol with sodium carbonate, does it give you a reaction? The answer would be no reaction. Sodium carbonate and phenol does not react. What about the carboxylic acid group directly attached to a benzene ring? We have benzoic acid here. So benzoic acid and sodium carbonate, what would you produce? What would you produce here? You'll be producing sodium benzoate, which is a salt. Apart from that, you will have carbon dioxide and water produced. Carbon dioxide and water will be produced. So students, when it comes to this type of reaction, you have to keep in mind how the reaction would take place. So if you are actually balancing this equation off to react with one carbonate, you would need 2 of these benzoic acids. So you'll be forming 2 sodium benzoates, 1 carbon dioxide and 1 water molecule. Now, they are asking us what can be produced when you are reacting salicylic acid with sodium carbonate. What can be produced? Now, students, can we have the phenol group reacted with sodium carbonate? The answer would be no. So, can we take the first answer that is given here? No, we can't necessarily take it because this is wrong. What about the second answer, B? Yes, actually, the carboxylic acid group can react with the sodium carbonate to form sodium carboxylate salt. So, because of that, the second one is actually correct. And you can see the phenol group did not react. Third one indicates that both of them have reacted, which is something that will not happen. Although the carboxylic acid group reacts, phenol group will not react. So therefore, C is also wrong. And the question is asking what can be produced. Can carbon dioxide be produced? Of course, yes. You have the carboxylic acid group here. So carboxylic acid group will react with the sodium carbonate, or the carbonate anion will produce carbon dioxide and water. We saw the reaction earlier. So carbon dioxide is definitely a product that can be produced. So both B and D answers are correct. So what is the correct answer for this question? We have different combination A and B, B and C, C and D, A and D, and finally B and D. So the answer would be B and D. The fifth answer is the correct answer for this question. Let's move on to the next one. Using the reagents listed below, suggest a series of reactions that will lead to the production of the compound given below. So we have a compound that is given to us, and then we have a few reagents that are given to us. Now, they are asking us to produce this particular compound using these reagents. So before we move any further, we have to identify what this compound is, or what two major compounds would have been used to produce this final product that we have at hand. And when you're observing, like always, you can see the ester group that is produced here, indicating if you have an ester bond like the ester bond that we have here, we can realize that this would have been formed by reacting a carboxylic acid with an alcohol. So we have, onto the left hand side, we have our carboxylic acid. And onto our right hand side, this part would have come from alcohol, from an alcohol group. So now, students, we have identified what were the two main compounds that would have gone into producing this final compound that we have at hand. Now, we have to take a step further and identify how to produce each of these things that are given to us. First one, we are only given one organic compound here, and starting with that compound, we have to produce the carboxylic acid and the alcohol we need to carry out this reaction. So let's take a look at how we can convert this acetaldehyde that we have given here, into a carboxylic acid. So we have CH3, CHO. How can we convert an aldehyde into a carboxylic acid? We can easily do it by oxidizing it. Do we have the necessary reagents for oxidizing it? Let's see. We have PbR3, we have magnesium, we have ether, we have dilute sulfuric acid, we have sodium borohydride, and then we have potassium dichromate and sulfuric acid. So basically, potassium dichromate is going to be an oxidizing agent when we have acidified it. So we can use dilute sulfuric acid along with potassium dichromate. So we can write dil H2SO4 and potassium dichromate K2Cr2O7. You will be producing CH3 COOH. You'll be producing the carboxylic acid we need over here to produce this final product, right? So we see the carboxylic acid is reacted to produce the alcohol, and the remnants of the carboxylic acid we can see here, it's CH3COO, and with that we can actually identify this would have been CH3COOH, or in other words, acetic acid. And we have now produced the acetic acid that we wanted. Let's move on to identifying the alcohol. So you can see over here, what we have is our alcohol. We have OH, C, CH3, CH, CH2, CH3. So this is the alcohol we need to produce. Basically, it's an alcohol with a carbon chain consisting of 4 carbon atoms, right? And OH group is connected to the second carbon. It's 2-butanol. So when it comes to this particular alcohol, how can we form that alcohol? Starting with the only organic compound that is given here is ethanol. Starting with ethanol, we have to produce 2-butanol.
So when you're trying to produce 2-butanol starting with ethanol, you have to think of the fact that whether we can produce it using aldol condensation. You're going to end up with a aldehyde and an OH group in two different places, which is going to complicate things. And then if you can think a bit further, you can look at the reagents that are given here, and you will observe that they have given you magnesium and dry ether, and there's PBr3. Maybe they are hinting at us that we have to use the Greenard's reagent. So we can, before we use the Greenard's reagent, we need a OH group that can be replaced by a Br group by the addition of PBr3. So first of all, the aldehyde should be converted into an alcohol. How can we convert an aldehyde into an alcohol? We have a reducing agent given here, sodium borohydride. So we can take, now in the second step, now this is the first main reaction where we produced our carboxylic acid, and the second main reaction can start now, where we take our aldehyde and we can react it with one sodium borohydride. Since they haven't given us methanol and water here, we can resort to using diel sulfuric acid. And you'll be forming CH3, CH2, OH, ethanol. You'll be forming ethanol. Now, after forming ethanol, we can use PBr3 to attach a bromine here. You'll be producing a halogen alkane, bromoethane. Now, of course, it should be quite clear to you what we are going to do next. We can add magnesium in dry ether because they have given you magnesium and dry ether. You are going to produce MgBr or Greenard's reagent, CH3, CH2, MgBr. So at this point, there's going to be a delta negative charge here, delta positive charge here, because when it is next to magnesium, the CH2 group that we have over here tends to have a negative charge, which can cause it to act like a nucleophile and attack the aldehyde group. So after forming the Greenard's reagent, if you react this with the aldehyde that we were provided, which is ethanol, you can produce the following, which is CH3, COMGBr. Basically, when this CH3CH2 group, I will highlight it with a different color, right? So this CH3CH2 group, this carbon, CH2 carbon, it will get attached to this carbon, and the carbon-oxygen double bond will break, and the electrons pertaining to one of those bonds will be given to oxygen. And MgBr will be positively charged, so oxygen is negatively charged and MgBr is positively charged. So therefore, there will be
connected together, and this CH2CH3 will come and join here. So this CH2CH3 is present here now, and this carbon originally had hydrogen, and that hydrogen still remains. So now we can see at this point we are halfway there to developing the alcohol that we want, and the final step to getting the alcohol would be adding an acid, would be to add an acid. We can add dill H2SO4 because they have given us dilute sulfuric acid, which will form CH3 COH over here, CH2 CH3. So students, what you have here is 2-butanol. So we have produced 2-butanol as we wanted. The alcohol that we wanted is produced, and after producing this alcohol, we can say this is the main product, second main product that we wanted. So initial main product was the carboxylic acid. This is our alcohol, right? So if you take this particular alcohol we have produced and react this alcohol with the carboxylic acid, right? We have the carboxylic acid here. I will write the carboxylic acid that we have produced over here, CH3 COOH. If you react these two together in the presence of concentrated sulfuric acid, we know when you're trying to form an ester, you have to use concentrated sulfuric acid and heat. You'll be forming this ester, CH3 C double bonded oxygen, and there's another oxygen here. And then we have, since the alcohol has the OH group connected to the second carbon, we have a CH3 group present here. So this is first carbon, and the second carbon you have the OH group. So when the OH group is connected to the second carbon, you can see a CH3 group is going to be present as a branch. And then you're going to have the remainder of the hydrogens, or remainder of the carbon and the hydrogens, present as CH2 and CH3 here. So this was the final compound that we were trying to form. And to form that, we took this path. We initially started with forming the carboxylic acid that we needed, which is acetic acid. We could easily form it by taking dilute sulfuric acid and taking potassium dichromate. So together we have acidified potassium dichromate, which is acting as an oxidizing agent. So aldehyde will be oxidized to carboxylic acid. And then we took the aldehyde and we were trying to convert the aldehyde into 2-butanol. So we took the aldehyde and we converted into an alcohol, which is ethanol, with the use of sodium borohydride and dilute sulfuric acid. And the ethanol or the alcohol was converted into a halogenol alkane with the use of PBr3. And we use magnesium and dry ether to convert that bromoethane into a Greenhouse reagent. And then with the use of Greenhouse reagent and the aldehyde that was provided to us, we converted it into the alcohol that we wanted. But before we do, we get an intermediate step with MgBr attached to the oxygen. Because of the negative charge on the oxygen and positive charge of the MgBr,
and then we can actually add a proton onto oxygen, removing the MgBr part by adding dilute sulfuric acid. So now we have formed 2-butanol, and the carboxylic acid we produced in the previous step together when reacted in the presence of concentrated sulfuric acid can form the final product that we aim to have. Let's move on to the next question. Complete the reaction series below by writing suitable compounds inside the boxes and suitable reagents inside the circles. So we have a reaction that is given to us, and we need to write suitable reagents inside the boxes and suitable reagents inside the circles. Students, like I always tell you, before starting your answers, before starting to answer this question, always observe the final product that you need to form. So we are starting with a benzene group that is connected to an ethyl group, which we can observe here as well. We can see this same group over here. And then we see another section. So you can see this carbon with double bonded oxygen is directly attached to this particular benzene ring. And as you know, alkyl groups when attached to a benzene ring are ortho paradirectors, and you can see this group is connected to the ortho, not the ortho, para position of this particular benzene ring. So now we have to identify what group can actually get connected to this benzene ring to form this final product. So as you can see, you would have, actually before we move on to that, I want you to be reminded about a specific type of reaction. We know when it comes to benzene, you can add a CH3 group directly to benzene by taking halogen group, reacting it with anhydrous AlCl3. What did we call this? We call this Friedel-Crafts alkylation reactions. This will lead to directly attaching the CH3 group here. Now similarly, students, we also learn about another type of reaction that is called Friedel-Crafts acylation, where acyl chloride groups can be added to the benzene ring. So if you take benzene and take an acyl chloride, let's take an acyl chloride like this, and react it in the presence of anhydrous AlCl3, you will be producing this particular compound. This is a C, right? You can see the carbon double bonded to oxygen is now directly linked to the benzene ring, finally forming a ketone. So when it comes to a situation like this, you can see, or when it comes to a question that we have been given here, a similar situation can be observed.
we have a carbon double bond to oxygen directly linked to the benzene. So we can obtain this by forming or by carrying out Fiedel-Crafts acylation reaction. But we have to take this compound and convert it into what we need to connect here first. So first of all, let's identify what we need to connect here. So to attach this group, to attach this group into this benzene ring, we would want to have this particular acyl chloride. We need to produce this particular acyl chloride. Now you can see the NO2 group is connected to a meta position. So that also should be something that you should look at. So if you start by keeping this alkyl group and then straight away going to nitration and adding the NO2 group over here, you will not be correct, because when it comes to alkyl groups, there are ortho-para directors, which means if you're adding the NO2 group, it will get connected to a ortho or a para position. But we want to get it connected to a meta position. So therefore, you cannot use nitration in the first step itself. We can, however, start by oxidizing. You can start by oxidizing this alkyl group that we have here. If we zoom it in a little bit, we can do this a little bit better. So let's first of all oxidize this ethyl benzene into benzoic acid. So if you use acidified potassium permanganate, H plus, KMnO4, you'll be able to get to benzoic acid. Now benzoic acid is a meta director. So therefore, if you are now carrying out the nitration reaction, it will, or the NO2 group will attach to a meta position. So let's do that. Let's attach a NO2 group into this benzene. So you can use concentrated H2SO4 sulfuric acid along with concentrated HNO3. You will be forming this compound. Right, so after forming that, we can use PCl5. We can use PCl5 to replace the OH group here and form an acyl chloride. We will replace that OH group with a Cl, and we will be forming an acyl chloride. I will continue to write all the reagents in red color and the products that we form in each step in blue color. So now we have formed an acyl chloride. So at this point, all that is left for us to do
is connect the acyl chloride and the ethyl benzene with the use of anhydrous aluminium chloride. We can use anhydrous AlCl3 to get to the final product. So now students, we have completed this conversion. We can see we started with ethyl benzene, we oxidized it to form benzoic acid, and then only we moved on to adding the NO2 group to the benzene ring, because NO2 group should be added to a meta position. After that, we can use PCl5 or PCl3 also can be used for this. And then when you use PCl5, the OH group of the carboxylic acid will be replaced by a Cl, forming an acyl chloride, which we have over here. And you can then carry out Friedel-Crafts acylation reaction by adding this acyl chloride to ethyl benzene in the presence of anhydrous AlCl3, forming this final product. So this is how this particular conversion can be carried out. Let's move on to the next one. Now we come to the 8th question. Indicate how 2-butanone can be produced using acetylene, C2H2, as the only organic compound. So you can't bring in any other organic compound. However, you can use any reagent. So let's move on to that question. So we are starting off with acetylene, or the IUPAC name is ethine, and we are going to form 2-butanone, CH3, C double bonded O, CH2, CH3. So this is 2-butanone. Now students, you have to form 2-butanone starting with acetylene. So when it comes to producing something like this, you can see the number of carbons have doubled, and the only organic compound that is given to you has only 2 carbons. So number of carbons have doubled. You can't use any other organic compound also. So that means this compound should be turned into something that can be added together to form this final compound. So we can actually think of something like allyl condensation. Again, allyl condensation would not end up giving an aldehyde and end up giving us a ketone. So you can't you can follow it to a certain degree, but you can't complete the conversion that we want here in a fewer number of steps. So we have another option where we can use Grignard's reagent. We can convert this acetylene into an aldehyde, and then aldehyde can be converted into an alcohol, where it is converted into a Grignard's reagent, and aldehyde and the Grignard's reagent can come together to form an alcohol, which can be oxidized to form the ketone. So we can have a secondary alcohol oxidized to form this ketone. So what would the secondary alcohol be if you want to oxidize it to produce a ketone? If you can form this particular alcohol starting from acetylene or ethine, you can actually get to the final product that we want. So now let's discuss a way that we can actually get to that particular alcohol. Like mentioned earlier, we can use Grignard's reagent. It is not an organic compound. We can't use organic
compound, the only organic compound that we can use is given here. So we will be using mercury sulfate and sulfuric acid, and we can use water and heat to convert this into an aldehyde. We have created an aldehyde here, and then we can convert this aldehyde into an alcohol easily by reducing it. You can use lithium aluminium hydride or sodium borohydride. Sodium borohydride and methanol together can convert this ethanol that we have into ethanol. And ethanol can easily be converted into bromoethane with the use of PBr3, or HBr also can be used. We will be using PBr3 here. You can convert it to CH3, CH2, Br. Then, if you add magnesium in dry ether, you can convert this into a greenhouse reagent. If you react this greenhouse reagent with the aldehyde that we have formed in one of the previous steps, you will be forming this. And by adding dilute sulfuric acid, you can get rid of this MgBr part that we have over here, and you can form 2-butanol. After forming our 2-butanol, we can oxidize it with the use of acidified potassium permanganate, or you can use acidified potassium dichromate as well. If you oxidize it, you will end up with 2-butanone. Now students, this is how the conversion can be done. You can start with mercury sulfate, sulfuric acid, and heat it in the presence of water, turn it into an aldehyde. Aldehyde can be reduced to form the alcohol. Alcohol can be turned into a halogenoalkane, and greenhouse reagent later on. You can react the greenhouse reagent with the aldehyde that we formed to produce an alcohol that is capable of getting oxidized to form 2-butanol. So students, when it comes to a question like this, especially when the carbon number is increasing, please resort to using techniques like greenhouse reagent or the use of greenhouse reagent to increase the carbon chain's length. So with this, we conclude the questions that are revolving around carboxylic acids. Students, with this question, we conclude the questions revolving around carboxylic acids. We started off with discussing the theory revolving around carboxylic acid. Then we moved on to the labs and conducted the experiment, and we came here to discuss some questions to improve your knowledge about how to answer questions that are revolving around carboxylic acids. I hope this has been useful. I'll see you again in the next experiment.